Transportation plays an important role in our everyday life. As the population is increasing, the need of automobile is also increasing to fulfill our requirements. As per the data available, 99% of all the vehicles uses internal combustion engine as its powertrain. The emissions caused by these vehicles is damaging the air quality in a catastrophic manner and at an alarming rate. The only chance we have is to seize this environmental catastrophe by replacing the ICE vehicles with electric vehicles in no time. This solution can affect 30% of the environmental problems, which will lead humanity to a cleaner and greener future. With countries targeting to reach full electrification of transportation system by the end of 2030, most of the vehicle manufacturers announced increasingly ambitious electrification plans. Out of the world's top 20 vehicle manufacturers, which represented around 90% of new car registration in 2020, 18 have started plans to widen their portfolio of models and to rapidly scale up the production of light-duty electric vehicles. The model availability of electric heavy-duty vehicles is also broadening, with 4 major truck manufacturers indicating an all-time electric future. Consumers' spending on electric car purchase increased to nearly $120 billion by the end of 2020, with most vehicles sold under the category of passenger vehicles. Foreign investors would be investing in India to build a fully sustainable electric infrastructure with new manufacturing hubs and increased push to improve charging infrastructures. India will be having various federal subsidies and policies favoring deeper discount for Indian-made electric two-wheelers as well as boost for localized ACC battery storage productions and other growth drivers for Indian EV industries. Moreover, in September 2021, a production-linked incentive scheme for the automotive sector was approved by the cabinet to boost the manufacturing of electric vehicles and hydrogen fuel cell vehicles. The blooming Indian EV market needs skilled employees for rapid growth and sustainability. For that, the Ministry of Skill Development and Entrepreneurship, the blooming EV market needs skilled employees for rapid growth and sustainability. According to the estimate of Ministry of Skill Development and Entrepreneurship, the EV industry alone will create 10 million jobs by 2030. For every direct job, there will be 5 indirect jobs in the society. This takes the number of total employment by the EV industry about 50 million. Industries will be needing employees under scientific research team, design and development team, manufacturing, maintenance and infrastructure for various EV sectors. So what should an employee have or know in order to get into all these sectors? What are the skills that the employee should possess to get into these sectors? An employee should know EV at system level, EVs at subsystem level. They should have a specific specialization depending on the industry. They must have a right guidance from industry experts. They should carry out projects, both hardware and software projects. They should simplify the problems that are generally faced by any EV industry. They should be aware of all the tools used in industries. They should get an internship from a very good skill sector and also must have a good mentorship. Taking into consideration, this master hybrid course is designed to provide you all the required skills needed to get into any industrial sector. In this promotional session, we will be covering some of the introduction to EV, energy storage systems for EV, electrochemical batteries, battery packs and BMS, with electric vehicle propulsion system, motor technologies and vehicle geometry with vehicle packing. To get the full course details, please visit www.skyrider.com/masterhybrids. Hello everyone, we'll be starting on with the first module of this course, that is the energy storage system. We have discussed about what are the things that we will be covering in this course. Out of all those things, the first thing, or you can say the primary thing that we have to know before knowing any electric vehicle or any hybrid electric vehicle, that is the energy storage system. The primary energy storage system for EVs are batteries. For for any type of electric vehicle, the primary energy storage system is batteries. See, we are discussing about a hybrid electric vehicle that doesn't solely runs, you can say it doesn't solely runs on engine. Engine is there only for backup. If the charge of the battery is exhausted, then engine can be used in order to regain or recharge the battery. And sometimes engine, or you can say engine can be used. We will also discuss about some of the vehicles where engine can be used as a drivetrain, means it can be connected to the drivetrain. But mostly we will be discussing about hybrids where engine is used only for recharging the battery. This is the reason why the primary source of energy for electric vehicles are batteries. So let us know about batteries. What is a battery? A battery is a source of electric power consisting of one or more electrochemical cells with external connections for powering electrical and electronic devices such as mobile phones, flashlights, electric cars, etc. Batteries accept, stores and release electricity on demand. Battery uses chemistry in form of chemical potential to store energy. You can say in here we have some examples like logs store energy in their chemical bond until burning converts the energy to heat. That means what? That means you can say the trees, they accept the carbon dioxide and convert that carbon dioxide into various forms of organic compounds, and they store those compounds inside them. When we cut that tree and we use that tree for let's say burning purpose or for generation of heat, then the organic compounds that are stored inside the tree gets converted to heat energy when we burn it. And the main thing you can say why it still continues to burn even if the source, or you can say the source that we have used for to start the fire is removed. Let's say we have used a matchbox or we have used any lighter in order to light the or lit the log, but still it continues to burn when we remove the external energy source medium. Why is that? It is because the amount of energy that is released when the compounds break is more than the amount of energy that is needed in order to break. This is the reason why the process continues for a long time. The same thing for gasoline engine also. You can say the gasoline is stored as chemical potential energy until it is converted into mechanical energy in a car engine. The same thing for gasoline also. The amount of energy that we need in order to break a molecule of gasoline is smaller than the amount of energy that is released. This is the reason why we have, or you can say why the burning process is continuous. For batteries to work, electricity should be converted into chemical potential form before it can be readily stored. You can say we recharge the battery. During the recharge of the battery, the electrical energy is converted to chemical potential energy and it is stored inside the battery. And during discharge, the same chemical potential energy is converted to electrical energy. We will be discussing about those things, how batteries stores discharge and release discharge. We will be discussing about those things in upcoming slides. Batteries are an attractive choice for EVs because they exhibit high energy density and a long life cycle. We have seen that there are generally two types of energy. One is energy storage, two types of energy storage. You can say we came across generally two types of energy storage. Other types of energy storage are also there, but those systems are yet not developed to be used in electric vehicles, such as nuclear energy. In order to harness nuclear energy so that it can be used in electric vehicles, it is not yet that developed. So in our day-to-day life, we come across two types of energy storage systems or energy delivery systems. First one is a fuel-based energy delivery system. Another one is a, or you can say, stored energy-based energy delivery system. Fuel-based means it is also, the energy is also stored, but the energy is released in a certain cycle. But in batteries, the energy is not released in any cycle. You can say we can continuously release the energy. The energy is already there. We don't have to produce the energy. In fuel, or you can say in fuel type systems, we have to produce the energy. Energy is there, but it has to be converted, and it has to be, we have to produce the energy in order to utilize it. Means we cannot directly use the fuel for any type of energy uses, but we have to produce or we have to extract that energy that we can use. But in batteries, already energy is there that can be directly used in order to run our devices. This is the reason why batteries are very attractive choice for EVs. That means we don't have to go for any, you can say, means the total number of stages that are there for power delivery, it is completely reduced. From battery can be directly connected to the converters directly to the power electronics. Supply is, or you can say, very smooth. You can say in engines we have lot of things. We have, you can say, the fuel has to be, engine is also simple, remember. Till, or you can say till date, engines are very simple to work. We can build engines, we can design engines, we can do anything with engines. But the power delivery stages are too high for an engine. Hence, there is a lot of mechanical loss. From your piston to your crankshaft to your gearbox, then to wheel. So, mechanical losses, a lot of mechanical losses are there. Hence, batteries are very good choice for EVs with a direct connection to driveline. That means batteries, converters, motors. Batteries, converters, power electronics and motors. Loss is very low. So, what are the various components of a battery? Batteries consist of two electrical terminals called the cathode and the anode, separated by a chemical solution called the electrolyte. What is a cathode? A cathode is an electrode where the electricity flows out of or given out. It is a negative side electrode and acts as an electron acceptor. Reduction reaction takes place at the cathode in an electrolytic cell. In order to fully understand how a battery works, we have to know how a galvanic cell works. Before that, let us know some of the key terms or some of the components that are used in any standard cell. The first one is a cathode, and reduction reaction takes place at cathode. The second one is the anode. An anode is an electrode where the electricity moves into. It is the positive side electrode and acts as an electron donor. Oxidation reaction takes place at the anode in an electrolytic cell. Electrolyte, it serves as a medium that allows the movement of ions between cathode and anode. Electrolyte is composed of salts, solvents and additives. Electrolyte are created in a way to allow movement of ions to electrodes and doesn't let electrons to pass. Remember, ions move inside the electrode. Ions, they move inside the electrolyte. But the electrons flow in the external circuit. The electrons, they flow in the external circuit and ions flow in an electrolyte. This is the reason why there is a continuous process of energy generation in batteries. So, let us know more about how battery works. We know that when a battery is connected to a device, it runs that device. Let's say if a battery is connected to a light bulb. If a battery is connected to a bulb, then it powers the bulb. If we have a on off switch, when we switch on the power, you can say the bulb glows. Why is that? When we switch it on, let's say the state is on state. The state is on state. The bulb glows. Why is that? It is because the energy that is stored inside the battery creates a potential difference. It is just like potential energy. We calculate the potential energy that is there in a body from the equation mgh. That means mass multiplied by the acceleration due to gravity multiplied by the height. That means when we increase the height, the potential energy also increases. In the same way, the energy that is there inside the battery creates a potential difference. For which electrons starts to flow from the negative terminal of the battery. And it returns back to the battery through the positive terminal. So if I name these things, you can say this is my negative terminal and this is my positive terminal. The electrons, they flow from the negative terminal of the battery. If I just represent the flow diagram or flow direction, this is the flow direction. Current flows from positive to negative. Electrons flows from negative to positive. Remember. So because of a potential difference, the electrons starts to flow. From Ohm's law, we can calculate what will be the current that will flow through this circuit, or what will be the value of current that will flow through this circuit from Ohm's law. What is Ohm's law? V is equal to IR. V is the potential difference of the circuit or potential difference that is available. Now, depending on the amount of resistance of the circuit, we can calculate the value of the current that will flow through this circuit. If the resistance is high, then current flow is low. If the resistance is low, current flow is high without affecting the potential difference. Clear? If the potential difference is very low, obviously very low current will flow and the device may not run. The device that are used with batteries, we can say we have to match their specification. We have to match the specification of the device with respect to the battery. So this is how a normal or general battery works. Now let us know what is happening inside the battery. What is happening inside the battery? Inside the battery, there are two half reactions or two half regions, because it is a redox reaction, means reduction and oxidation takes place simultaneously inside the battery. One of the reaction takes place at any one electrode and the other reaction takes place at the other electrode. So batteries, they have electrodes also. These are the electrodes of the battery. It has two electrodes. Depending on the type of reaction that occurs on these electrodes, we name them as cathode or anode. Let's say this is a copper zinc based cell or galvanic cell. copper zinc based cell. This is a copper electrode that we are using in here. This is a zinc electrode, This is a zinc electrode that we are using in here, and this is a copper electrode that we are using on the other side. Then we need to have electrolyte. What is the use of electrolyte? We will discuss. Now, this zinc and copper are connected to a external circuit, because cell, we want to measure the energy output of this cell, because we are building the cell so that we can have an energy output. So either we can connect a meter in here. Let me just connect a meter. A voltmeter. That will measure the potential difference of these two half cells. Now we know zinc very easily loses electron. If I go for zinc plus 2 electrons, zinc very easily loses electron, so it becomes zinc ion plus 2 electrons. So what is happening with zinc? It is oxidizing. Or oxidation reaction is taking place. I am sorry if the spelling is wrong. Oxidation. Zinc oxidizes while copper reduces. If I write copper 2 plus 2 electrons gives rise to copper. The elements in their neutral form, has 0 oxidation and reduction number. The elements in their neutral form has 0 oxidation and reduction number, but when they oxidize or reduce, they have specific oxidation reduction number, generally represented by a oxidation number. In here you can see zinc gets oxidized to zinc ion. So the oxidation number for zinc increases. Copper ion reduces to copper metal. So the oxidation number for copper decreases. Now zinc very easily can oxidize to give off 2 electrons, and copper very easily can accept 2 electrons to give out copper metal. So now this reaction can start. If we just connect it, it will show some readings. Zinc is getting oxidized and copper is getting reduced. Zinc is getting oxidized and copper is getting reduced. But after some time, what will happen? After some time, since zinc is losing electrons, so a positive charge starts developing on this side. On this side. And copper is gaining electrons. So negative charge will, no negative charge will develop in here. No negative charge. It will become neutral. With no charge. But positive charge will be developed on the side of zinc. Now when the positive charge is developed on the side of zinc, then we can say zinc will no longer ionize. It will no longer, or you can say electrons will no longer flow out of this zinc electrode because of, you can say, increase in positive charge. Now how this charge can be balanced? If I just use this system as a battery, then for 1 to 2 seconds it will run, then it will shut down because of equilibrium condition. That means it is reaching equilibrium condition very fast. If my batteries or cell will reach equilibrium condition very fast, then I cannot use those things for a longer period of time. If I want to run a device, if I want to run a motor, if I want to run a laptop that has to run for 4 hours, 5 hours, then I can't use this cell or I can't use this design. So in that condition, what we generally do, we connect both of these half cells with a salt breeze. With a salt breeze. Okay, with a salt breeze. Now what is the use of this salt breeze? This salt breeze is used to balance the charge. Now zinc ion, where is zinc ion? You can say when zinc loses electron, you can say it when zinc loses electron, so it will come out of the electrode. When it is losing electron, that ion you can say cannot be present freely in an electrode. So it will come out. So where it will come out? It will come out to an electrolyte. And the electrolyte must be stable enough to store zinc ion or to allow zinc ion to move inside it. If the electrolyte is not strong or if the electrolyte is not a stable electrolyte, that means when zinc is getting converted to zinc ion, the electrolyte will react with the zinc ion and to produce, or you can say it will produce any other compound. So that will not work. Hence, we have to use an electrolyte that can fully sustain the zinc ion without any reaction. So, the electrolyte that we use for zinc or on this side, or you can say for zinc electrode is ZnSO4, zinc sulfate. In the same way, copper, what will happen to copper? Copper ion when reduces gets converted to copper metal, so that gets deposited over here, the copper gets deposited over this region. So now where we get, or we can say from where we will be getting this copper ion? We will be getting that copper ion from the copper electrolyte, or you can say from this electrolyte, from a electrolyte that is copper sulfate. Remember, copper is getting deposited on the electrode while zinc is coming out of the electrode. That means when this reaction will continue for some time, this zinc electrode will lose its mass while this copper electrode will gain some mass. Okay. Now what will happen in here? You can say if I have connected a salt breeze, what is the working of this salt breeze? Remember, when we have copper ions in here, then we have sulfate ions in here also. We have sulfate ions in here also. And in here also we have zinc ions. Sulfate ion is negative, zinc ion is positive. So in order to balance the ions inside the electrolyte, the salt breeze will allow flow of Zn ions and sulfate ions. Zn ions and sulfate ions. Okay. Now if you ask, sir, why this flow is taking place? It is only because of electric field. We know when electric field is neutral, the charge are not drawn towards the electric field. But when the electric field is not neutral, then there is flow of charge. Electric field, we know electric field that if a positive potential is there, then the electric field moves out of that positive potential. If a negative potential is there, then the electric field goes into the negative potential. This is the reason why the ions flow across these half cells. Okay, the ions flow across this half cell because of two things, concentration difference and electric field. Concentration difference and electric field. Both of these drive the flow of ions. Now, there is no additional accumulation of charge in here. Why? Because the zinc ion is getting, or you can say it is flowing to the other side of the cell, while the sulfate ions are flowing to this, you can say, to the or near the zinc electrode, for which now this reaction will not reach equilibrium for a longer period of time. That means we can utilize this cell for a longer period of time. Means it will not be reaching equilibrium very fast, rather it will be reaching equilibrium slowly, and it will take some time, let us say 1 to 2 hours to reach equilibrium. Before it was reaching equilibrium very fast. Why? Because of accumulation of charge. Now there is no accumulation of charge. After some time, when you can say we have enough zinc and enough copper in both of the side, and the salt breeze is not able to allow the flow of ions, again we have a discharge state or a equilibrium state. But that equilibrium state, these two half cells, you can say, in order to reach that equilibrium state, these two half cells will take a long time, or you can say longer time than without this salt breeze. So this is how our cell work, or you can say works. You can say we have electrolytes, we have electrodes, and we have salt breeze. Generally we don't have any salt breeze. Sometimes in you can say the electrolyte, or you can say both of them are completely connected. We have a similar electrolyte that will provide, or you can say that can accept the ions from my, you can say, okay. So in here, one thing I have left out. What will be the cathode and what will be the anode? You can say in here, if I just see the reaction, zinc is the anode because oxidation is taking place, while copper is the cathode. This is what I was showing you there. Zinc is the anode and copper is the cathode. So nowadays, the batteries, or you can say the batteries that we use, both of the electrolytes can be mixed. That means actually we use a single electrolyte that has both the compounds. It has both the anode compound and also the cathode compound. So that if anode is giving out its ions, those are stable inside the electrolyte. If if the cathode is accepting the ions or accepting the ions, I will be saying, then also it is stable. Clear? I think we are all clear with the working of battery. Next we will go for our static energy, that is electrolytic capacitor. The secondary energy storage devices that are used on electric vehicles are capacitors. Capacitors generally stores static energy, and you can say the type of capacitors that are used in electric vehicles or hybrid electric vehicles also, those are electrolytic capacitors. Capacitors are electrical components that stores energy and are widely used in electronic devices. Supercapacitors are named for their ability to store more electrical charge than standard capacitors. It stores charge physically through the buildup of charges on their surface. This is how a capacitor stores charge. It stores charge through charge buildup on the plates that are used inside the capacitors. The charge are stored on the surface of the plates. We will discuss how a capacitor works in upcoming slides. Pseudocapacitors can store charge chemically through redox reaction when one species transfer electrons to another, similar to a battery. We will also discuss the working of a pseudocapacitor. Pseudocapacitors, you can say, they are new type of batteries. But the only problem is, it also charge and discharge very fast. Pseudocapacitors can store as much charge as some of the batteries. However, battery charges and discharges over several hours, while pseudocapacitors can operate much faster on the scale of tens of seconds to several minutes. Supercapacitors often show high power density and long operation lifetimes, but are limited by very low energy density. You can say the supercapacitors, they have very high power density. That means they can deliver the energy that is contained in it very fast. Energy delivery of those capacitors is very fast, but the amount of energy that those capacitors can store is very low. Pseudocapacitors store more energy. Their widespread use has been hampered by narrow electrochemical voltage window, which is the voltage range when the electrode material are stable. Like our batteries, in our lithium-ion battery, we have a potential difference of 3.7 volts. If we use the same potential pseudocapacitor, or you can say if we want to implement a pseudocapacitor in place of that lithium-ion battery with a potential difference of 3.7 volt, then the pseudocapacitor has to be very large. These are the reasons why the uses of pseudocapacitors are hampered. And what is that? That is the narrow electrochemical voltage window. Electrolytic capacitors are most common form of static energy storage in an electric vehicle. Graphene supercapacitors also exhibit the potential to act as the primary power source of an electric vehicle due to their short recharge time and relatively high power density. We'll discuss about graphene supercapacitors also. Now, let us know how capacitor works. We know capacitors have plates and those plates are connected to a voltage source. Those plates are connected to a voltage source. This is the positive terminal of the battery and this is the negative terminal of the battery. The negative terminal is rich in electrons and the positive terminal has deficiency of electrons. So what will happen? In this capacitor, we will have electron accumulation on one of its plate that is connected to the negative terminal and positive charge accumulation on the other side of the plate. If we remove this potential difference or if we remove this voltage source, now the charge has no path or no return path to reach equilibrium or to flow to the negative side. Generally, the electrons, in order to neutralize the charge, the electrons will flow through this direction towards the positive charge. Now the potential difference is removed. So, or you can say this is an open circuit in here. When the potential difference is removed, this becomes a open circuit. Now through this open circuit, the electrons can't flow. So now we have a charge buildup. We have a charge buildup. And when we use this capacitor or when we connect this capacitor to any device, then the capacitor discharges to that device, powering that device for a certain period of time. Now, how do we increase the efficiency of the capacitor? Let's say I am using this capacitor, it has a certain surface area. Let's say surface area is A. It has a surface area of A. If I increase the surface area, then what will happen? the amount of electrons or the amount of charge buildup will also increase. When we increase the surface area, the charge buildup will also increase. And what are the other ways? If we reduce this distance d, then also the efficiency of capacitor increases. Why is that? The potential difference decreases. When the plates are further apart or when the plate are at a distance, if the potential difference is V, then if we reduce the plate distance, then the potential difference reduces, for which the capacitance of the capacitor increases. If I write the formula for capacitance of the capacitor, C is equal to Q by V. C is equal to Q by V. We also know that the capacitance also depends on area. Capacitance is directly proportional to area and capacitance is inversely proportional to the distance between them. If we write the formula, then we have a constant. And what is this constant? This constant is nothing but the permeability of the material. So C is equal to the permeability of the material A divided by D. So these are the two formulas that generally governs the capacitance of the capacitor. So in order to increase the capacitance, what we have to do? Either we have to increase the area or we have to decrease the distance. The area can be increased. Okay, the area is increased now. The distance can be reduced. Okay, the distance is reduced. Now let's say the distance is d by 3. We have reduced the distance. Previously the distance was d, now the distance is d by 3. Now we have an increase in capacitance. Now still we can further increase the capacitance by including a dielectric. Why do we have to use a dielectric in capacitor? Because dielectric generally we know that yes, dielectric increases the capacitance of the capacitor. But how do dielectric increase the capacitance of the capacitor? There are some of the things. We cannot increase the area of the capacitor further. Why? Because capacitors are used in very small electronic devices. Also big electronic devices and small electronic devices. If we increase the area, then the size of the capacitor will also increase. If we increase the distance, again the size of the capacitor will also increase. So we can up to certain threshold, up to certain size threshold, we can increase the area and we can decrease the distance. Still, we are not getting, or you can say, the total efficiency of the capacitor is not yet reached. Even if we are designing the capacitor up to a certain threshold, but still we are not getting the efficiency of the capacitor. If you say, sir, how can we find out the efficiency of the capacitor? Efficiency of the capacitor can be found out from the amount of potential difference that is used and the amount of charge buildup that we get for that potential difference and the amount of charge buildup that can be further increased or that we can actually get theoretically and amount of charge buildup that we are getting practically. By comparing these two, we can find out that still we are not able to reach the efficiency of the capacitor. So now there is another option. If we reduce this potential difference, now I have certain distance between the plates. This distance also increase the potential difference between the plates. If the distance is longer, then the potential difference is also high. Why is that? If you just compare these two equations, this is equation 1, this is equation 2. The potential is directly related to the distance. The potential is directly related to the distance. So if more the distance, more the potential difference. But we cannot reduce the distance any further because we have already reached a threshold. So in that reason, or in that condition, what we can do is we can include a dielectric. We can include a dielectric. So what will the dielectric do? The dielectric is generally a non-conducting material. It is generally a non-conducting material. But when we insert a dielectric between two plates, what will happen? There will be charge separation within the atoms. That means we will be having small atoms inside the dielectric, and those atoms will have a charge separation. That means negative side and positive side. Those atoms will have a charge separation. You can say there will be no flow of charge. Physically, there will be no flow of charge. But we will be having a charge separation because of the potential difference or charge accumulation that has taken place on those plates. Now what is happening in here? The distance between the charge or distance between the two polars or negative and positive charge has now decreased. The total distance that we are having in between the two plates, now that distance is less, or the distance has decreased by inserting a dielectric. Now since the distance has decreased between the charges, or you can say between the two polars, the potential difference will also decrease. And when the potential difference decreases, the capacitance increases. When the potential difference decreases, the capacitance increases. This is the reason why we have dielectric in between capacitors. In supercapacitors, in order to increase the capacitance, because supercapacitors, their energy density must be very high. This is what you can say. I was talking about a general capacitor, but supercapacitor means their energy density must be very high. So how do we generally increase the energy density for a supercapacitor? The energy density is increased by, you can say, increasing or by coating the plate with porous material. By coating the plates with porous material. Now the porous material will have a increased surface area. It is just like a solid ball. If you just take the solid ball, then we only have to take the outer surface area, a solid ball, a ball made out of metal. Then we just have to take the outer surface area, that is the total surface area that is available for that ball, if we take a solid ball. But if we take a porous ball, if the ball is porous, means it has holes in here. Now, if we calculate the total surface area of this ball, including the porous, then obviously the total surface area will be much bigger. It has a surface area, let's say A1, and this porous ball has a surface area of A2. So if we want to include the surface area of this ball of same diameter but with porous face, then we'll have a increase in surface area. So this is the reason why when we coat the plates, the capacitor plates with porous material, graphene, generally graphene or any other porous material, then the total surface area of the plates increases, because now the porous regions also have a surface area. The porous regions also have a surface area. If we just take into account the flat portion of the plates, then the surface area is bit less. But if we include the porous region of those plates, then we have an increase in surface area. Now in pseudocapacitors, not in pseudocapacitors, in supercapacitors, the plates are generally coated with porous material and that increases the surface area, for which the capacitance of those supercapacitors increases. That means when the capacitance increases, the amount of charge it can hold also increases. Now the energy density also increases. So this is how we generally increase the energy density of a supercapacitor. More the new the supercapacitor is, more the efficient the plate deposition is. New supercapacitors, or you can say recent supercapacitors, they have a very good dielectric and very good plating or coating on their plates. Now this brings to an end to how supercapacitor works and how supercapacitors are developed. We will talk much about the pseudocapacitors in upcoming sessions. How pseudocapacitor works and how a pseudocapacitor can be compared with a lithium-ion battery. Thank you. Hello everyone, welcome back. In the previous session, we have discussed what are the various energy storage devices or systems that are available to be used on an electric vehicle. We have discussed about batteries, capacitors and supercapacitors and their working. In today's session, we will discuss what are the various types of electrochemical energy storage devices that are available. We can say the performance of energy storage device can be defined by their output and energy density. Energy storage devices can be used for uninterruptible power supply, transmission and distribution system on a large scale generation depending on the technology applied on the storage capacity. Battery technology for energy storage devices can be differentiated on the basis of energy density, charge and discharge efficiency, lifespan and eco-friendliness of the device. So what are the various types of electrochemical energy devices that are available? First one is a battery, second one is a capacitor. Also, fuel cells are also included in electrochemical energy storage device. We will be discussing about fuel cells in upcoming sessions. The basic form of electrochemical energy storage device is a battery. You can say the performance of energy storage device can be defined by their output and energy density. That means if the energy density of the device or the storage device is very good, then it can last longer. If the output is very good, then it can run heavy loads or it can work with very heavy loads. So these two things are very important for any type of electrochemical energy storage device. First one is the output, second one is the energy density. Output, you can say, what does the output decides? Output decides what is the load that can be connected or what is the amount of load that the energy storage device can work on. And energy density. Energy density means how much energy can the device store. Energy storage devices can be used for uninterruptible power supply, transmission and distribution systems support on a large scale generation depending on the technology applied on the storage capacity. In this session, we will discuss about the cells that make up that build up the energy storage devices, electrochemical cells. So what is a cell? What is an electrochemical cell? The most fundamental unit of battery pack is a electrochemical cell. The power storage device is a battery pack. Actually, in electric vehicle, the power storage device, the primary power storage device is a battery pack. And those battery packs are built out of small individual cells. What should be the property of these cells so that they can be used to create a battery pack? All performance characteristics are dependent on the material inside the cell and all cell works according to some general principle independent of the material employed. They work according to some general principle. Those principles are set up by the designers cell designers and also the control system designers. That what are the rules that the cell should follow? The cell designers set those rules of building a cell, or you can say when they will be building a cell, they set those rules, and those who use those cell, they also set some rules. And those rules are generally used in the control systems. An electrochemical cell converts chemical energy when discharged and vice versa. The basic design of an electrochemical cell consists of a positive and a negative electrode separated by an electrolyte. The basic design. You can say how a battery is designed, in the same way a cell is also designed. And a battery can be a combination of two or more cells. The chemical reaction taking place during the charge and discharge process are based on electrochemical oxidation and reduction reaction known as redox reaction. The same for a battery also. What we have studied about battery, the same for cell. Why is that? Because cell is an individual unit of a battery. Battery is an electrochemical energy storage device, and the cells are individual components of a battery. Electrons are transferred via external circuit from one electrode to another, and at the same time ions are transferred inside the cell through the electrolyte to maintain the charge balance. The species oxidized are called oxidants and the species reduced are called reductants. This is a simple electrochemical cell, a lithium-ion cell with a potential of 3.7 volt. The lithium-ion cells are arranged in modules, 444 batteries or cells in a single module. Again, those modules are arranged to create a battery pack. 16 battery modules or 7104 battery pack, or you can say batteries or cells, make up the total Tesla S battery pack. So cells, in here we can know that cells are individual component of a battery pack. Why do we have to use cells? Why can't we build a battery pack with all those you can say chemicals completely building up the battery, or completely covering the battery, or completely being used inside the battery? Why can't we go for such things? It is because if any small failure occurs on the battery, then the whole battery system has to be changed. And battery system, they are using lithium ions, they are using gold platings, and you can say gold, they are using very costly metals for which battery packs are very costly. If we replace the whole battery pack, the consumer has to spend a lot of money. If there is a single problem also, we can't fix the battery pack because we have to completely tear it apart in order to fix it, and that will ultimately damage the battery. Hence, those options are not provided to the consumer. Rather, what we can do is, we can make a battery pack that can supply us with nearly 300 volts to 800 volts of potential difference. And we get this potential difference by arranging cells in modules and modules in battery pack. So that if any problem occurs inside the battery pack, then a module, the affected modules can be replaced, or the affected cells can be replaced. Another important criteria of using cell is the stability of the battery pack. If we are using cells, then we can monitor individual cells and the stability can be maintained by monitoring those cells. What are the things that we have to monitor in a cell? The cell potential, the cell current, the state of charge of the cell, and the temperature of the cell. The cell potential, the cell current, and SOC along with the temperature of the cell. When we monitor these things of a cell, we can very well maintain the stability of the battery pack. Let us know about different types of cells that are available. Different types of cells that are available to create modules and modules to create battery pack. So first one is a lead acid battery or lead acid cell. Lead acid battery means the whole battery pack is made out of or built out of lead acid cells. This type of secondary cell is widely used in vehicles and other applications requiring high value of load current. Its main benefit are low capital cost, maturity of technology and efficient recycling. Lead acid batteries nowadays you can say nowadays means from 2012 to 2019 or even 2020 or even 2020. All the two-wheelers and three-wheelers electric vehicle that we see, all of them consist of lead acid battery. Any type of two-wheeler and three-wheeler vehicle, electric vehicle that we see on the market that are running on the road, they all have lead acid battery. Why is that? It is because lead acid battery is a mature technology. Lead acid battery is a mature technology. Most of the automobiles use lead acid battery. And most of the devices also use lead acid battery, like your inverters, household inverters, generators, automobiles, they use lead acid battery. Hence the technology is very mature. If we implement those batteries in our, you can say, new electric vehicles, then the cost will be very low. So these are the benefits of using lead acid battery as a lead acid cell or lead acid battery with lead acid cells. Low capital cost, maturity of technology, and there is very good recycling of lead acid batteries also. If you have a, let's say, the two-wheelers, the two-wheeler consumers, their battery pack or their lead acid battery is damaged. So what they can do? They can just replace the battery pack. Means they will be returning the batteries to the supplier. And the supplier will be providing them with new batteries with reduced cost if they are returning the battery. If they are not returning the battery, then the supplier will maintain its cost. But if the consumer is returning the battery, the damaged battery, then the cost reduces. Because those things can be very efficiently recycled. The advantages of lead acid battery: low cost and simple to manufacture, low cost per hour, you can say whatever, that means charging of those batteries also consume very less amount of energy, high specific power, capable of high discharge current. They have very high specific power. And what is this high specific power? High specific power means they can supply energy very fast. High specific power means they can supply energy very fast. Good performance at low and high temperature. No block-wise or cell-wise BMS required. These are some of the advantages of lead acid battery. What are the disadvantages? Low specific energy, poor weight to energy ratio. Specific energy means, what is specific energy? The amount of energy that the battery can store is the specific energy of the battery. Lead acid batteries, they have a very good specific power. That means they can discharge a lot of current, but that they cannot store a lot of charge. Okay. They can discharge a lot of current, but they cannot store a lot of charge. That is what is a disadvantage of lead acid battery. And poor weight to energy ratio. What is this poor weight to energy ratio? Those batteries, since they are using lead is a very dense metal. So the weight of those batteries is very high. So the amount of energy that can be stored in the given volume and the amount and the battery weight, that ratio is not that good. Another disadvantage is slow charging. these batteries charge very slow. Why is that? It is because if we use high charging current, then these batteries will bulge, or this battery may get, or you can say it will be completely damaged if we charge this battery with very high charging current. Fully saturated takes about 14 to 16 hours. It takes a long time to charge. Need for storage in charged condition to prevent sulfation. If the batteries are charged, then the storage should be proper, or else there will be sulfation. Sulfation means the electrodes, or you can say there will be impurity in the electrolyte. Sulfate impurities in the electrolyte. Limited cycle life, repeated deep cycling reduces battery life. We can say limited cycle life. They can only be charged and discharged up to a certain cycle, and that cycle time is very low. These lead acid batteries, they can be charged and discharged up to a certain cycle, and that cycle is very low. Nearly 300 to 400 cycles. Repeated deep cycling reduces battery life. What is this deep cycling? Deep cycling means, let's say your batteries are completely charged up to 100%, then they will be discharged to nearly 5% and sometimes beyond 5%. Again they will be charged to up to 100%, again they will be discharged to 5%. So that is deep cycling. That means fully charged, fully discharged, fully charged, fully discharged. And this deep cycling reduces battery life. And some of the batteries, they require water requirement, or you can say they are flooded types. Some of the batteries are flooded type. That means we have to use distilled water inside those batteries. Then transportation restriction for flooded types. If the battery is utilizing water or distilled water, then there is transportation restriction in those batteries. Let us see the chemical reaction that governs the lead acid battery. This type of secondary cell is widely used in vehicles and other applications requiring high value of load current. Its main benefits are low capital cost. Obviously, we have discussed about these things. So, what is the reaction that governs the lead acid battery chemistry? Lead plus H2SO4 gives rise to lead sulfate, hydrogen ion and 2 electrons. Since we are losing electron, so this is anode. Oxidation is taking place, the reactants are losing electron. So oxidation is taking place because we have 2 additional electrons on the right hand side. Hence the reaction has to be at the anode side. At the cathode, lead oxide plus 3 hydrogen ions along with the sulfate ion plus 2 electron that is received from the anode. You can say, if I just draw the diagram, the electrons flow from the anode to the cathode. You can say the electrons flow from the anode to the cathode, and at the cathode side, lead oxide along with the hydrogen ion. This hydrogen ion, how this hydrogen ion is on the at the cathode side? The hydrogen ion was transported through the electrolyte. The electrons are transported through the external circuit, while the hydrogen ions, the sulfate ions are transported through the electrolyte. Now, we get a complete reaction, that is lead plus lead oxide plus sulfuric acid or H2SO4 gives rise to lead sulfate plus water. So, left to right is discharging, left to right this is the discharging direction, and right to left is the charging. For these batteries, the specific energy is nearly 35 to 40 watt hour per kg. Energy density is 80 to 90 watt hour per liter. Specific power is 80 watt per kg, whilst and cycle durability is nearly 350 cycles. Then types of lead acid batteries. We have sealed or maintenance free lead acid batteries, starter batteries for your stator motor, and deep cycle batteries. So what is a sealed or maintenance free battery? First appeared in mid 1970s. Engineers deemed the term sealed lead acid as a misnomer because lead acid batteries cannot be totally sealed. Remember, the batteries, if we seal those batteries, then there is a problem. What is the problem? It is because any element, when it heats up, not any element, some of the elements, when it heats up, they tend to change their state. Obviously, it is true for all the elements. If it is lead, if we apply heat to lead, lead will change its state. From solid, it will become liquid. From liquid, it will become gas. So, gas generation is, you can say, gas generation is not mandatory, but gas generation is must for all type of batteries. That means there will be some generation of gas, since electrolytes are present in semi-liquid or liquid form. So when those electrolyte heats up, they change their state. From liquid state, they get converted to, or you can say they change their state to gaseous state. Hence, if we seal those things, then we know that when gas is build up, or when there is gas build up, then there is lot of pressure build up also. So if we seal the batteries will just boom, it will just blast out. Hence, ventings are always required for any types of battery or cells that we design. Ventings are always required. The Tesla cell that we are seeing over there, that lithium-ion cell, those also have vents and some, you can say, disconnectors or some contactors that gets disconnected when there is excessive gas buildup. To control venting during stressful charge and rapid discharge, valves are been added to allow the release of gas if pressure builds up. So this is a sealed or maintenance free lead acid battery. Maintenance free means we don't have to maintain the battery. The battery electrolyte will be, if the battery electrolyte is damaged, then the complete battery is damaged. But in some of the batteries, we can again refill the electrolyte. Those are maintenance batteries. Now, if a lead acid battery is termed maintenance free, that means we cannot update, or we cannot again you can say use, or we cannot replace the electrolyte, or we cannot change the electrolyte, or we cannot add the electrolyte. It is completely maintenance free. If there is any problem in the battery, the whole battery has to be discarded. Then stator batteries, designed to crank an engine with momentary high power load lasting for seconds or so. If for its size, the battery delivers high current, but it cannot be deep cycled. The stator batteries cannot be deep cycled. What I was saying about deep cycle? Deep cycle means batteries are fully charged and fully discharged. Deep cycling or deep discharge occurs beyond the safety threshold. When we discharge the battery beyond 5%, then it goes for deep discharge. Once the battery is deep discharged, again recharging the battery becomes very difficult. We cannot recharge those batteries through standard chargers. We need to use additional tools or additional devices to recharge those batteries. And you can say on the end of the consumer, those tools are not available. You have to go to a service station, battery service station, and they will be helping you to again recharge the battery if the batteries are deep discharged. Deep discharge means discharging beyond a safety threshold. 5% is the safety threshold for your battery. If the batteries are discharged beyond 5%, then the resistance of the battery increases and we cannot discharge those batteries, or we cannot recharge those batteries using standard chargers. Hence, if these stator batteries are deep discharged or deep cycled, then the life of these batteries reduces. Built to provide continuous power for wheelchairs, third one is a deep cycle battery. Built to provide continuous power for wheelchairs, golf carts and forklifts, among others. This battery is built for maximum capacity and a reasonably high cycle count, used for certain devices like wheelchairs, golf carts and forklifts. Uses of lead acid battery. Sealed lead acid batteries are generally used in UPS, emergency lighting systems, wheelchairs, because of its low price, dependable service and low maintenance requirement. The SLA, that is sealed lead acid battery, remains the preferred choice for healthcare in hospital and retirement homes because there is no gas generation also. The sealed lead acid battery does not produce any harmful gas. Though vents are there, okay, but the vents will be releasing, you can say will be open when there is excessive gas buildup, and we can see the gas buildup. The vents will open at a certain threshold only. It will not open, you can say the vents will not be active throughout the life cycle of the battery. It will just be active at the end of certain life cycle or at the end of certain threshold. Hence, no harmful gas generation. But our maintenance batteries, they have a lot of gas generation. You can say the inverter batteries that we use, or the batteries that the batteries that can be refilled with electrolyte. Those batteries release a lot of harmful gas. Valve regulated lead acid battery, VRLA battery, designed to crank an engine with momentary high power load lasting a second or so. For its size, the battery delivers high current, but it cannot be deep cycled. Absorbent you can say glass material used for lead acid battery. Absorbent glass material is a semi-solid electrolyte or semi-liquid electrolyte. Built to provide continuous power for wheelchairs, golf carts and forklifts among others, this battery is built for maximum capacity and a reasonably high cycle count. The next variety of cell that is used for building the battery packs are nickel-cadmium cells or nickel-cadmium battery. The nickel-cadmium battery is a rechargeable battery used for portable computers, drills, camcorders and other small battery operated devices requiring even power discharge. So what are the advantages of using a nickel-cadmium cell to build a battery pack? First one is rugged high cycle count with proper maintenance. That means these batteries, they have a very high cycle count. Previously, we have seen that our lithium-ion batteries, lead acid batteries, they are having a cycle count of nearly 350 cycles. That means they can go for charge discharge cycle of 350 times or 350. They have a charge discharge cycle of 350. 350 doesn't mean that you can say nearly 175 charging, 175 discharging. No, 350 means it is 350 charge discharge cycles. Only batteries that can be ultra fast charged with little stress. You can say this type of nickel-cadmium batteries or these nickel-cadmium batteries, they can be very fast charged with very little stress. That means we can use we can use high charge current or high charging current in order to charge these batteries without any buildup of stress. Good load performance, forgiving if abused. Long shelf life, can be stored in a discharge state needing priming before use. What is this priming? Priming means cell conditioning. Priming means cell conditioning. That means when we store a cell for a long period of time, then some of the electrolytes, or you can say the electrolytes generally gets deactivated, not deactivated, you can say the mixtures, you can say sometimes the electrolyte is a mixture, so the mixture settles and we have to again activate those mixtures. So that is priming. Priming means we generally activate the cell if it has been stored for a very long amount of time by using certain tools. Hence, you can say these nickel-cadmium batteries, they have a very long shelf life. That means they can be stored for a very longer amount of time. And before using those cells, we have to prime those cells or we have to condition those cells. Simple storage and transportation not subjected to regulatory control. Lead acid batteries generally are subjected to regulatory control, but nickel-cadmium batteries are not subjected to any kind of regulatory control. Good low temperature performance. That means this type of batteries can be used in a very low temperature condition. Economical pricing. Nickel-cadmium has the lowest cost per cycle price. availability in a wide range of sizes and performance options. These are some of the advantages of using a nickel-cadmium battery as a battery pack. Or these are some of the advantages of a nickel-cadmium cell. What are the disadvantages of you can say this nickel-cadmium cell? Relatively low specific energy compared to newer systems. Obviously, they have a very low specific energy. Just like lead acid batteries, they also have a very low specific energy. That means we cannot store a lot of energy inside those cells. Power delivery is very good, for which they can be very fast charged and discharged. But amount of energy that these batteries can hold is very less. Memory effect needs periodic full discharge and can be rejuvenated. So what is the memory effect? Memory effect means, let's say if you have used a battery in a certain device, then the battery has memorized the working of that device. If you just replace the battery, or you can say, let's say now you just take out the battery from that device and you are using the battery in any other device, then the battery may not work properly. May not work means what will be the deviation or what will be the difference? Difference is in, you can say, working time. If in any one device the batteries was providing a run time of 1 hour, in the other device it may provide a run time of 35 minutes or 40 minutes or something less than the or anything less than the previous device, because it has memory effect. It has memorized the working of the device in which it was being used. Cadmium is a toxic metal, can be disposed of in landfills, cannot be disposed of, sorry. Cadmium is a very toxic device. That means if you use nickel-cadmium battery and those batteries are leaking, then it can cause cadmium poisoning. It is a very toxic metal and the disposal of cadmium is also very problematic. High self-discharge needs recharge after storage. These batteries gets discharged when they are stored for a long amount of time. Just like lead acid batteries, these batteries also have high self-discharge. That means if the battery is completely charged and it is kept for a very long amount of time, then it will be discharging itself. So again, we have to recharge those batteries before, you can say, before we start its use. Just like when you buy a new UPS, in those UPS there will be a, or you can say there will be a sticker. On that sticker it will be written that please recharge the battery for 6 to 8 hours before use. Why is that? It is because of this high self-discharge of lead acid batteries and some of the nickel-cadmium batteries. Low cell voltage, 1.2 volt, requires many cells to achieve high voltage. So the nickel-cadmium chemistry produces only a potential difference of 1.2 volts. Hence, in order to get the required potential for our battery pack, we have to use a lot of cells. So what is the chemistry that generally governs the nickel-cadmium batteries working principle? Nickel-cadmium battery, it is a dry cell rechargeable battery using nickel oxide hydroxide and metallic cadmium. The chemical reaction at the cadmium electrode during discharge are: the cadmium reacts with the hydroxyl ion, produces cadmium hydroxide and 2 electrons. Since this is a oxidation reaction, so it is taking place at anode. This is a oxidation reaction. Why? The species are losing electrons. Hence, this is a oxidation reaction and it is taking place at the anode. The reaction at the nickel oxide electrode, at the cathode, nickel oxide hydroxide receives 2 electrons through the external circuit along with the water that is present in the electrolyte, gives out nickel hydroxide and 2 hydroxyl ions. Now these 2 hydroxyl ions are again transported to the cadmium electrode through the electrolyte. The net reaction during discharge is this: cadmium plus 2 nickel oxide hydroxide plus water gives rise to cadmium hydroxide and nickel hydroxide. So when this reaction continues, then we have a continuous supply of energy from the batteries. What is the specific energy for this battery? 40 to 60 watt hour per kg. Energy density is 50 to 150 watt hour per liter. Specific power 150 watt per kg. The cycle durability of these batteries, it is nearly 2000 cycles. In lead acid batteries, we have a cycle durability of less than 350. But these nickel-cadmium batteries, they have a cycle durability of 2000 cycles. After that, the another variety of battery pack cells are nickel metal hydride batteries. So why do we need to use, or why do we have nickel metal hydride batteries? It is because cadmium is a very toxic metal. Hence, the cadmium metal is replaced by any other metal in the nickel metal hydride battery. The nickel metal hydride battery combines the proven positive electrode chemistry of sealed nickel cadmium battery with the energy storage features of metal alloys developed for advanced hydrogen energy storage concept. Positive electrode chemistry means we are getting a positive energy, just like Gibbs energy. If the Gibbs energy is positive, then it is spontaneous. If the Gibbs energy is 0, then it is a neutral reaction. And if it is negative, if the Gibbs energy is negative, then it is a non-spontaneous reaction. If it is positive, spontaneous, negative, neutral, and 0, neutral, and negative means non-spontaneous reaction. So the positive electrode chemistry means this is a spontaneous reaction that is taking place inside the battery, for which the energy is released at a very high rate. That means the power density. Since it is very spontaneous, the power density is very high. Nickel metal hydride batteries outperform other rechargeable batteries and have higher capacity and less voltage depression. These nickel metal hydride batteries, they have a very high capacity than their previous generation batteries, like nickel cadmium batteries and lead batteries or lead acid batteries. And they have a very less voltage depression. What is this less voltage depression? When we start drawing current from the batteries, then the voltage reduces. Why is that? Because the potential difference, when there is a charge, positive charge and a negative charge, the charge, the potential difference completely depends on the distance between the two charges. The potential difference depends on the distance between the two charges. When we start to, when the current starts to flow, then the charge separation is reduced. The distance between the two charges are reduced, for which there is a drop in potential. But if you say that, sir, then the potential should be reduced to 0, it does not reduce to 0. Why? Because the current that is flowing is not very high. If the current is too high, then the potential reduces to 0. We call that as a short circuit. That means all the charge that is there in the battery is flowing to the other side. Hence, the potential difference is completely reduced to 0. That means very high current is flowing. But when the current is being discharged at a very controlled rate, then the potential depression is very low. That means we have a charge of, let's say, x coulomb, and the charge that is flowing, this x coulomb of charge, this x coulomb of charge creates a potential difference of, let's say, 24 volts. If we flow nearly x by 1000 coulombs of charge, then the potential may come down to 21 or 20 volts. If we flow all the charge or the x coulomb of charge, then the potential completely reduces to 0. Hence, the current, potential depression completely depends on the current and the amount of charge that is getting produced in the chemistry of the battery. In this nickel metal hydride battery, the amount of charge that is getting produced is very constant and it is very stable. Hence, the voltage depression is also very less. The nickel metal hydride battery currently finds widespread application in high-end portable electronic products, where the battery performance parameters, notably the runtime, are major consideration in the purchase decisions. So, what are the advantages of this nickel metal hydride batteries? First one is the energy density, which can be translated into either long run times or reduction in space needed for battery. These nickel metal hydride batteries, they have a very good energy density. That means they can store a lot of energy as compared with their nickel cadmium battery and lead acid battery. Elimination of constraints imposed on battery manufacturer uses and disposal because of concerns of our cadmium toxicity. Since we are not using any cadmium in here, hence there is no problem of disposal of these batteries, even recycling of these batteries. Simplified incorporation into products currently using nickel cadmium batteries because of the main design similarity between the two chemistries. Any of the product that is working on nickel cadmium battery can be replaced with this nickel metal hydride battery because both of them have similar chemistry. Greater service advantage over other primary battery types at extreme low temperature operation of nearly minus 20 degrees Celsius. So, these batteries can work in minus 20 degrees Celsius also. If you ask, sir, what happens to a battery? We know that when the battery temperature increases, then the battery will burst or there is a problem in SOC. But when the temperature decreases, what will happen? The same thing. When the temperature decreases, now the battery is, or you can say, the battery supplies most of its energy to the surrounding because of very low temperature. When the thermal gradient between the ambient temperature and the battery is very high, since most of the energy is lost in heating the battery or maintaining the thermal gradient. If the thermal gradient is very high, remember, if the battery is working at room temperature, thermal gradient is very low. Hence, the battery can use most of its energy to carry on the chemical reaction and to generate electrons. But if its energy are getting dissipated to maintain the thermal gradient or to maintain the temperature of the reaction, then we have a very less SOC of the battery. That means the batteries are discharging very fast, or else the batteries are not generating enough electrons to be used, for which the current is reducing. At extreme low temperature operation means these batteries are unaffected by very high thermal gradient. What are the disadvantages? Limited service life. If repeatedly deep cycled, especially at high load currents, performance starts to deteriorate after 200 to 300 cycles. Shallow rather than deep discharge cycles are performed. For this nickel metal hydride battery, deep discharge will reduce the performance of these batteries. I have said about deep discharge. Deep discharge means discharging beyond a certain threshold. That means battery is fully charged, again it is completely deep discharged and discharged beyond a certain threshold. Then the battery's efficiency will reduce or the battery performance will start to deteriorate after 200 to 300 cycles. Hence, shallow discharge cycles are preferred. Shallow means the discharge, you can say the battery will be discharged up to 10% or 20% and it will be fully charged to 80% or 90%, not completely 100%, 80% to 90%. This is for discharge threshold. Charge threshold is 80% to 90%. These are shallow discharge and charging rates. If we perform the charging and discharging within these limits, then the performance of the battery, you can say, reduces very slowly or can be kept stable. Limited discharge current. Although a nickel metal hydride battery is capable of delivering high discharge currents, repeated discharge with high load currents reduces the battery's cycle life. Best results are achieved with load currents of 0.2 to 0.5 C, 1/5 to one half of the rated capacity. Need for a more complex charging algorithm. The nickel metal hydride battery generates more heat during charge and requires a longer charging time than nickel-cadmium battery. The trickle charging is critical and must be controlled carefully. What is this trickle charge? Trickle charge means if we continuously charge a battery, then the battery temperature will continuously increase because it is losing energy as heat. So if we continuously charge a battery with a specific amount of current, then the battery temperature will slowly increase also. But if we provide the current in cycles or in steps, that means for 1 second we provide some charging current, then we let the battery to cool down. Again we provide some charging current, again we let the battery to cool down. Again some charging current, again some charging current. So this is trickle charging. That means the charging current are sent in pulses or in steps. There is no constant supply of current. The current is not constantly supplied. Rather, it is supplied in steps or in pulse. This reduces the battery damage and also the heat generation in batteries. This is what trickle charging is. That means this is not a continuous charging process. This is a stepwise charging process. And the current and the potentials are maintained throughout the charging cycle or throughout the charging process. That means when the battery is completely empty, then high current is provided to the battery. When the battery is near full, then the current is reduced and the potential is increased. Okay. So that the battery life can be maintained and also the battery temperature can be kept stable. High self-discharge. These batteries also have high self-discharge. The nickel metal hydride batteries has about 50% higher self-discharge compared with nickel-cadmium. You can say these batteries have very high discharge. That means if you are just using it in a device and you have stopped using the battery or you have stopped using the device and the device is not discharging the battery, then the nickel metal hydride battery will discharge itself. New chemical additives improve the self-discharge but at the expense of low energy density. Now, in nickel metal hydride batteries, new additives are provided, but those new additives, they decrease the energy density of the battery. What is the chemical reaction that governs this battery? H2O plus the metal that is used plus the electron gives rise to hydroxide and metal hydride. So in here, this is a reduction reaction because the electrons are utilized. So this is taking place at cathode. On the positive electrode, nickel oxide hydroxide is formed. Nickel hydroxide that is present in the electrolyte plus the hydroxide ion gives rise to nickel oxide hydroxide plus water plus electrons. Since the species are, you can say, providing electrons or they are generating electrons, hence this reaction takes place at anode. Oxidation reaction, giving off of electron. During recharge, the reaction goes from left to right and opposite during discharge. Lithium-ion battery. The lithium-ion battery chemistry have the highest energy density and are considered safe. After nickel metal hydride battery, the next variety of battery is lithium-ion battery. And the lithium-ion battery chemistries have the highest energy density and are considered safe. Lithium-ion batteries, a lithium-ion cell have a cell potential of nearly 3.7 volts, while our lead, they have nearly 1.5 to 2.1 volts. And this is for lead acid battery. And for nickel batteries, 1.1 to 2 volts. But for lithium ion batteries, it is nearly 3.7 volts. This is the reason why these batteries have a very high energy density. That means they can keep a lot of charge, or they can store a lot of charge, and those charge can produce a potential difference of 3.7 volts. No memory or scheduled cycling is required to prolong battery life. Lithium-ion batteries are used in electronic devices such as cameras, calculators, laptop computers and mobile phones, and are increasingly being used for electric mobility also because of their high energy density and fast charging and fast discharging also. That means they have both high energy density and high power density also. High specific energy and high load capabilities with power cells. Long cycle and extended shelf life, maintenance free. This is not self, this is self. Long cycles and extended shelf life, maintenance free. High capacity, low internal resistance, good Coulombic efficiency. We have studied about lithium-ion cell chemistry in the previous sessions, how the intercalation was taking place, how there is a porous separator that is used to transport the lithium ions from one side of the or from one half cell to the other half cell. Simple charge algorithms and reasonably short charge times. These are some of the advantages of lithium-ion batteries. Disadvantages: need for protection or need for protection circuit to prevent thermal runaway if stressed. What is this thermal runaway? Thermal runaway means when we can no longer control the temperature of the battery. Then we say that the battery has gone for thermal runaway. That means the temperature can no longer be controlled. This happens when the battery generally bulges to a certain threshold. There is any puncture in the you can say there is any puncture in the battery, or of the battery, you can say the electrodes, or there is a short circuit inside the battery. Then the battery goes for thermal runaway. That means we can no longer control the temperature of the battery. The temperature will continuously increase until all the charge that is there gets neutralized. Degradation at high temperature and when stored at high voltage. That means if we expose these batteries to very high temperature, then these batteries will degrade. It is only because lithium ions are intercalated with, or you can say the lithium ions are stored in intercalation. If high temperature, then the intercalation will not take place properly. Because the cobalt oxides will be, the lattice of the cobalt oxide will be vibrating very high, or we can say it will be vibrating too much. Intercalation will not take place properly. Hence, these batteries generally degrade at high temperature and when stored at high voltage also. Impossibility of rapid charging at freezing temperature. Same thing. When the temperature is very low, then it is nearly, we cannot recharge these batteries. Same thing, because lithium ions are stored in intercalation. When it is freezing temperature, again you can say the lattices will not allow the holding of, or will not allow the intercalation of lithium ions. Hence, nowadays some other types of lithium ion chemistries are used in order to create a very good and a stable battery. Need for transportation regulation when shipping in large quantities. Generally for LiPo batteries, lithium polymer batteries, there is a transportation regulation. Why? Because they can burst, or they can act as an explosive. The lithium polymer batteries, the LiPo batteries, they act as an explosive if not properly stored or controlled. Hence, there is transportation regulation for delivery of or shipping of lithium ion batteries. So, what are the different types of batteries that are available? The most common type of lithium ion batteries are lithium cobalt oxide batteries. These batteries consist of cobalt oxide cathode and a graphite carbon anode. The cathode has a layered structure. During discharge, lithium ion moves from the anode to the cathode. Anode is the graphene. Inside the graphene, we have LiC6 that gives out C6 graphene plus Li ion. Plus electrons. So this is at the anode. Oxidation is taking place, hence it is at the anode. And the lithium ion moves from the anode to the cathode through the porous separator. The flow reverses on charge. The drawback of lithium cobalt batteries is their relatively short lifespan, low thermal stability and limited load capabilities. Low thermal stability means when the temperature increases or decreases, there is problem in intercalation of lithium ions, for which the thermal stability of these batteries are very low. Limited load capabilities. These batteries can be used with certain type of loads, not all type of loads. Lithium ions with manganese spinel, which was first published in Material Research Bulletin in 1983. So the next type of lithium battery is lithium manganese oxide, LiMn2O4. And this type of batteries were first published in Material Research Bulletin in 1983. The architecture forms a three-dimensional spinel structure that improves the ion flow on the electrode, resulting in low internal resistance and improved current handling. A further advantage of spinel structure is high thermal stability and enhanced safety, but the cycle and calendar lives are limited. Remember, now for battery packs, or you can say for to be used in electric vehicles, the cells has to be very safe, or else the battery pack can be very fatal. If there is any fire in the battery pack, it can be very fatal. Hence, what is how we generally prevent all these things, or how we generally prevent the thermal runaway? We can prevent the thermal runaway. If there is thermal runaway, the battery will bulge and it will burst. But we have added certain fire retardant material in the casing of the battery. That means if the battery is catching fire, then the fire retardant material will remove the fire, or it will stop the fire. And the battery packs, the whole battery pack is, or you can say built with, or you can say we have a layer of fire retardant material in the battery packs and also in cells and also in modules. The whole battery pack is covered with fire retardant materials. So if any of the cell is catching fire, then the fire retardant material will prevent the spread of fire. The third type of battery is lithium nickel manganese cobalt oxide, or NMC battery. One of the most successful lithium-ion system is a cathode combination of nickel, manganese, cobalt. Cobalt is there for intercalation, nickel is there for stability, manganese is also there for stability of the intercalation at various temperatures. Similar to lithium manganese battery, these systems can be tailored to serve as an energy cell or power cells. That means this type of cells, they have a very good stability, very good energy density and very good power density, along with very good thermal runaway properties also. Because cobalt is used for intercalation, manganese is used for stability, manganese and nickel are used for stability of the lattices. You can say in various temperatures. Then lithium iron phosphate. In 1996, the University of Texas discovered phosphate as cathode material for rechargeable lithium batteries. Lithium phosphates offer good electrochemical performance with low resistance. This is made possible with nanoscale phosphate cathode material. The key benefits are high current rating and long life cycle, besides good thermal stability, enhanced safety and tolerance if abused. The final type of lithium-ion battery is a lithium titanate battery, generally used for space applications. Batteries with lithium titanate anodes have been known since 1980s. The lithium titanate replaced the graphite in the anode of a typical lithium-ion battery, and the material forms into a spinel structure, same as lithium manganese. The cathode can be a lithium manganese oxide or NMC. Lithium titanate has nominal cell voltage of 2.4 volt. The potential difference is very small, or it is less than the normal lithium-ion battery. Can be fast charged and delivers a high discharge current of 10 C. That means 10 times the rated capacity. The cycle count is said to be higher than that of a regular lithium-ion battery. The lithium titanate is safe and excellent low temperature discharge characteristics and obtains a capacity of 80% at minus 30 degrees Celsius also. Hence, this type of batteries, they are generally used in space application. The satellites that you see, the space rovers that you see, they are all built with, they all have lithium titanate battery in them. Then I have said you about the lithium ion, you can say lithium battery chemistry. This is the lithium battery chemistry, how the intercalation takes place, how the lithium ions are stored in intercalation, and how the lithium is transported through porous separator, and how the lithium is stored in graphene also. So this brings us to the end of this session. In the next session, we will discuss about EV battery packs. What are the things that are needed, or what are the rules that are needed to design a EV battery pack? We will be discussing about those things. Thank you all. Hello everyone and welcome back. So in the previous session, we have discussed what are the various chemistries that are used in batteries or different types of batteries, and also depending on the type of battery that we use, what should be the charging, discharging methods, and also the working environment that needs to be used for all those batteries. Now, in order to install those batteries in electric vehicles, we need a battery pack, or in order to install those cells, not batteries, in order to install those cells in a electric vehicle, we need a battery pack. It is because we need higher potential to run the system. Any system, even if it is a two-wheeler, three-wheeler or four-wheeler system, the amount of potential that we need cannot be provided by a single cell. This is why we have to assemble the batteries in modules and also the modules in battery pack. So how do we design a battery pack? What are the various processes that are involved in designing of a battery pack? So we will be discussing about those things in this session. So EV battery pack. EV battery pack is nothing but a housing for all the cells that will be assembled to provide us the required potential and current. A EV battery pack is a set of any number of identical batteries or individual battery cells. They may be configured in series, parallel, or a mixture of both to deliver the desired voltage. The battery pack high voltage system is designed to control power flow to and from the cell to maintain the power level within the design envelope. This accomplished through the use of following components. So what are the components that are used in battery pack? Battery pack has certain components. Those are fail-safe components. That means during the time of any failure or any uncertainty or unconditional extraction of power from the battery, then at those time these fail-safe methods will be active or will be activated by the BMS or by the controller of the battery pack. So first one is a contactor. They are electrically actuated switches that are primarily used to disconnect the battery pack from vehicle high voltage system when the vehicle is not in use. Contactors are also a safety item that can be opened to disconnect the battery pack if some part of the vehicle malfunctions and is forcing the battery pack outside its design envelope. So what are these contactors? Contactors are nothing but they connect the battery with the power system. They connect the battery with the power system or the battery pack with the system that will use the energy from the battery pack. So contactors are actually first layer switches that are used in order to connect and disconnect the battery pack. Then after we have a pre-charger circuit. Pre-charger circuit is a very important circuit that has to be installed in all the battery packs. Why is that? Let us see. As the battery pack closes, the contactors and transitions from a disconnected state to a connected state. You can say, as the battery pack closes means when the circuit is closed, when the connection between the system, external system and the battery pack is closed, then the contactors transit from a disconnected state to a connected state, and there is a possibility of momentary but very large currents. Obviously, there will be a very large current. Why? Because the potential difference that was maintained, it was not slowly, means we have not reached the potential difference slowly. We have reached the potential difference or we have connected the circuit very fast. Let's say if I draw a graph in here, let's say the potential was 0 when the circuit was open. When the circuit was open, there was some potential difference. Sorry, the potential is not 0. Okay, the potential is not 0. The current was 0. Let's see, the current was 0. Now suddenly the switch is closed. So there will be a spike in current. Because suddenly the whole system is active. And in order to run the system, a high amount of current needs to be drawn from the system. Hence there is a sudden spike in current. After some time, the spike reduces. After some time, the spike reduces. Then the optimum current that needs to be discharged from the battery pack is reached. But when the contactors close, there is a surge in current. Why is that? It is because, as we know, or you can say when the electrons are at a static state, they are not moving. Then in order to move them, we need more energy, and once they are in motion, then the energy that is needed is dropped. As you can say, it drops. So when we close the circuit, a very large current starts to flow, and this may damage the battery pack. So the transition must be a controlled process. That control is provided by the pre-charger circuit. Initially, when the circuit closes, the resistance of the circuit is very high, so that very less amount of current will flow. Slowly the resistance is decreased, so that we can reach the optimal current in a very smooth path, or the current will have a very smooth path to reach the optimal value without any spike. The third one is a fuse. A fuse is another important safety device. It is used to protect components from excessive current. Okay, it is used to protect components from excessive current. Manual service, then the fourth one is manual service disconnect. A fourth safety device used within a high voltage battery pack is called MSD, that is manual service disconnect. This device is a method for breaking the electrical continuity within the pack for the purpose of vehicle service. The MSD is often a touch-safe removable enclosure containing the fuse. That means in order to disconnect the battery pack from the rest of the system, during any service, any maintenance task, there is a manual service disconnect. That means we don't have to go inside the battery pack in order to remove the contactors, and then in order to dismantle the battery pack. We don't have to go for such things. There is a manual service disconnect. When we go use that manual service disconnect, the battery pack contactors are still intact, and we switch off the power flow from the battery pack. These are the 4 fail-safe systems that are installed in every battery pack. So how are cells arranged in battery pack? Cells are arranged in a variety of manner. Or you can say, there are infinitely variety of battery pack combination. There are infinitely variety of battery pack combinations. Most widely used combination for battery packs are ladder or linear or F-type combination. For small battery packs, for a battery pack that will drive a two-wheeler, for a battery pack that will drive, two-wheelers and e-cycles. For them, this ladder or F-type combination of battery pack is very good. We get the maximum volume. We get the, or we can arrange maximum or most amount of cells with a very small, in a very small volume. Or the volumetric efficiency, or not volumetric efficiency, volume efficiency is very good in this type of arrangement. D, you can say this is the formula for the volume. D is the diameter of the cell, H is the number of cell, H is the height of the cell. Then after that we have multi-row cell. Multi-row cell is used for heavy battery packs or a bigger battery pack, where we have to use nearly 20, 30 or even 40 cells to get the required potential and energy. Remember, why I am saying about potential and energy? Potential means the rate at which the energy can be utilized, and energy means the total amount of energy that is there in the system. So you can say it is arranged in this manner, multi-row cell. it is arranged in row wise manner, where we get the total effective volume as Nd multiplied by Md multiplied by H. Where D is the diameter of the cell, N is the number of cells in the row, M is the number of rows, and H is the height of the cell. The third and the most widely used you can say cell arrangement for large battery packs. Battery packs, that will be used in 3-wheelers, 4-wheelers and commercial vehicles, large commercial vehicles. Those are face-centered cells. These face-centered cells are arranged in modules, and modules are again systematically arranged to create battery pack. So, the total volume or the effective volume for this type of arrangement is the length, that is given by the formula N is the number of cells multiplied plus 0.5 whole multiplied by the diameter of the cell. W 0.866 multiplied by P. P is the number of row, minus 1 plus 1 multiplied by the diameter of the cell, and H is the height of the cell. In order to find out the effective volume, or in order to find out the total volume that will be utilized by this type of arrangement, we use this formula. So, these are certain type of battery or cell arrangement for BMS. Then there are heat sink tubings also. In battery packs where we do not use any type of cooling system. Cooling system means obviously there will be a natural cooling system that will be cooled, you can say using ambient air. But if there is no cooling jacket that is installed in the battery pack to aggressively cool down the batteries, then we use heat sink tubings to arrange the batteries in a proper way, so that they can be effectively arranged and also the cooling of those batteries can be effectively maintained or achieved. The most common way to hold the battery pack together is to use heat sink tubing. These heat sink tubings are generally used in 2-wheelers, e-cycle and some 3-wheelers battery pack, not 4-wheelers. 4-wheelers battery pack are arranged in certain other way. There we use a thermal resistant material. Thermal resistant material means the material will not change when the temperature changes. The properties of those material will not change, or the state of those materials will not change when the temperature inside the battery pack changes. And those thermal gels or thermal material that we use, they are very good conductor of heat, and they can dissipate the heat from the battery very effectively. We will be discussing about those things in upcoming sessions. These are sufficient strength for small packs, but as the weight increases, more structural strength is required. But I have said that this type of battery pack arrangement or this type of way or method of holding the cells to create a battery pack is only for small battery packs or medium sized battery packs. When the size of battery pack is very big, then these heat sink tubings are not recommended for those systems, or they are not helpful. Why? Because they will be deforming. These are made out of acrylics, cyanoacrylates. These are made out of cyanoacrylates, and there you can say strength is very good or optimal when the battery pack is small, but when the battery pack is very big, then their strength is of no use, or their strength does not match the required criteria. This is done by adding a sheet of structural material to the top and bottom of the pack. Sometimes, even if in 3-wheelers, we have to use more battery pack, or we have to use more battery pack, not battery pack, we have to use more number of cells in the battery pack. So, for that, sometimes we add some structural material, either a steel, reinforced steel, means we reinforce the steel, or you can say we reinforce these cyanoacrylates with steel linings, or some other plastic or acrylic, same acrylic materials of good structural strength. Another source of strengthening is to use glue when the cells touch each other. So, another way of strengthening this battery pack arrangement is to use glue. That means to stick the batteries using glue. so that the glue will provide the additional strength that is required in order to hold the cells together. Cyanoacrylates are sometimes used to stack things together but can weaken the Winley heat sink if not reinforced. So these heat sink tubes are generally made out of Winley, and cyanoacrylates are sometimes used. Cyanoacrylates are structural materials or liner materials. Those are used in order to provide the structural strength to this Winley heat sink. In large battery packs, battery holders are there. You can see a battery holder in here, and we can call this total, or you can say we can call this arrangement as a module. This module is installed in a specific manner to create a battery pack. A battery holder is one or more compartment or chambers for holding a battery or cells. For dry cells, the holder must also make electrical contact with battery terminals. For wet cells, cables are often connected to battery terminals, as is found in automobiles or emergency lighting equipments. When using or designing battery holders, there should be an adequate provision for short cells, long cells and wide cells. Keeping sharp clip edges from touching the cells, they would cut the film or paint, causing a short between the cells held by the same clip. Okay, you can see there will be some sharp edges like this, there will be certain sharp edges. So when we install modules, another module, if I will be installing another module on this side, okay, if I will be installing another module in the front of this battery in here, then those modules or these sharp edges can puncture the cells that the module is holding. So these sharp edges has to be removed properly, or they have to be taken care of in battery holders. Now we know how we can create a battery pack. Battery pack means how can we arrange cells in a battery pack. Now what are the types of cells that can be used in order to create a battery pack or in order to design a battery pack? Those are cylindrical cells, button cells, prismatic cells and pouch cells. These are some of the cell types that are used in order to create a battery pack. Of all these things, cylindrical cells are the most effective cell type. Why? Because of their ease of manufacture, good mechanical stability, tubular shape and minimized deformation. They are also fitted with a positive thermal coefficient device. What is this PTC device? Positive thermal coefficient. That means if the temperature of the battery increases, this positive thermal coefficient material's resistance also increases. So when the temperature increases, the resistance increases. So why do the temperature increases? When there is excessive draw of current. We can say when exposed to excessive current, the normal conductive polymer heats up and becomes resistive, stopping the current flow, acting as a short circuit protection. So that this positive thermal coefficient is a fail-safe device. The material that is used in order to build this positive thermal coefficient, they are resistive at high temperature or at high current, and they are normal, you can say they are conductive at room temperature or at an optimal temperature. Then there is a charge interrupt device also that are fitted in these cylindrical cells. This charge interrupt device is actually a permanent circuit breaker. This PTC device, positive thermal coefficient, is a temporary circuit breaker. When the current is very high, and when the current is high, there is an increase in temperature, this positive thermal coefficient opens the, or you can say breaks the circuit. But if there is excessive gas buildup, then this charge interrupt device will permanently disconnect the battery from the rest of the circuit, or it will permanently disconnect the cell from the rest of the cells. So these two things are fitted within most of the cells, and these two things are there in cylindrical cells also. Button cells, I will not be discussing about button cells. they are used in small electronic devices that are there in your vehicle. They are not a part of the battery pack, but they are sometimes used to monitor some things. Let's say you have a sensor, and the sensor cannot draw current from the battery pack, or else we have to keep the battery pack on for you can say for on throughout the working of the vehicle. Hence, some additional sensors are there that runs on these button cells. They do not, you can say they are not a part of the battery pack, or they are not the part of the module that are built out of cells. They are generally installed as an additional device, or you can say as an additional battery to control the sensors of the modules and battery pack. Then we have prismatic cells. Prismatic cells, you know, your cell phone cells and your small devices cells, they are all prismatic cells. Prismatic cells also are used for smaller battery packs. For bigger battery packs, these cells are not convenient. Why is that? It is because of the structure. These cells have various sharp structures, or you can say they are weak along their edges. Cylindrical cell has a very good mechanical stability, but this prismatic cell, they are weak around these structures. So when they bulge, the battery can fail from these corners. Hence, prismatic cells are not preferred for larger battery pack. They are preferred for smaller battery packs, but they are not preferred for larger battery packs. Then after we have pouch cells. Okay. We have pouch cells. Pouch cells are very good type of cell for commercial vehicle battery pack. Why is that? Because we can draw very large amount of current from these pouch cells. And you can say that, sir, why we can draw very large amount of current? Can't we draw the same amount of current from cylindrical cells? Actually, the pouch cell have a very large surface area. So when we draw a large amount of current, the heat that is generated with that current gets dissipated very easily. So the batteries will not be heating up, and that will prevent any damage to the battery. So pouch cells are the most preferred cells for commercial vehicles. Commercial vehicles where the battery pack can be kept detached than you can say from the driver compartment. That means if there is any failure of the battery pack, then the personnel or the driver that is driving the vehicle and the passengers also, they will not be affected. Hence they are used in large commercial vehicles. But in passenger vehicles, the battery pack, you can say, is directly below the compartment or sitting compartment. Hence, if there is any failure in the battery pack, it may affect the passengers and the driver also. But pouch cells, this is the reason why pouch cells are not preferred in passenger vehicles, because these are prone to failure. These are prone to failure because of these corners, as I have said. Because of these corners. Hence, they are mostly used in commercial vehicles. Hello everyone and welcome back. In the previous session, we have discussed what are the various functions that the BMS does in order to control a battery pack, or in order to maintain a correct operating or correct optimal performance of the battery pack. So, what we have discussed is, or you can say, a battery management system is an electronic system that manages a rechargeable battery, such as by protecting the battery from operating outside its safe operating area, monitoring its state, calculating secondary data, reporting data back to the user, controlling the working environment, authenticating and balancing the battery. So, in the previous session, we have discussed how a battery pack is designed. A battery pack is designed using individual cells, and cells are assembled to create modules, and modules are assembled to create battery pack. So now, we also know that no two cells are similar. All the cells are different from each other. And in order to monitor the performance or optimal performance of each and every individual cell, we need control units that will monitor the current, potential, state of charge, and also the temperature of the cells. In order to do all those things, you can say the Tesla battery has nearly 7,000, sorry, the Tesla battery pack has nearly 7,116 or 116 cells, 46 cells. So to control and monitor each and every individual cell is very difficult. It is not difficult, but it needs a very stable logic so that there will not be any type of imbalance between cells. If the cells are imbalanced, obviously there will be drop in performance of the battery pack. So these things has to be maintained properly. For those things, certain functionality, objectives and rules of the battery management systems are set. That means under what rules, under what objectives the battery management system will work. Depending on those rules and objectives, the performance of the cells are optimized. So let us know about those rules and objectives of the BMS. So objectives of BMS. According to the definition, the basic tasks of the BMS are identical to its objectives. Although different types of BMS have different objectives, a typical BMS follows these three objectives. What are those objectives? It protects the battery cells from abuse and damage. It extends the battery life as long as possible. It makes sure the battery is always ready to be used. So these are the objectives that the battery management system has to fulfill. These objectives can be fulfilled by controlling certain parameters. And for controlling those parameters, some of the rules and functions of the BMS are defined. We know objectives. Objective means what? Objectives are nothing but goals. So these are some of the goals of the battery management system. That means all the parameters that the battery management system is controlling, the main objective of controlling those parameters is to reach these goals. That means it should protect the battery cells from abuse and damage. It should extend the battery life as long as possible. By controlling those parameters has to be tuned in such a way that these objectives will be reached with very high efficiency. Finally, it makes sure the battery is always ready to be used. All the parameters, what I have said, how we can tune all those parameters that are monitored, that are controlled by the BMS to reach these objectives. So let us know some of the functions of BMS. How do BMS work on those parameters or work on some of the parameters in order to define certain functions, and thereby the functions, or by you can say working on those functions, it can reach a certain objective. So first function of the BMS is discharging control. The primary goal of a BMS is to keep the battery from operating outside of its safety zone. All the cell manufacturers, they provide a safety limit for the battery. That means what should be the maximum discharge current, what should be the maximum charging current, what should be the maximum charging potential, and you can say the deep discharge limits. All the manufacturers, they provide all this data, and those data are fed to the BMS so that the BMS will always try to keep the cells within its safety zone. The second function of the BMS, or second function of the discharging control of the BMS must protect the cells from any eventuality during discharging, preventing the cells to operate outside its limitations. When the cells are discharging, the cell current varies. Sometimes the cell current is very high, sometimes the cell current is very low. The problem is when the cells are discharging, you know that when current flows in any system, when we try to change the flow of current, there is always a resistance in the system. Sometimes when the current spikes are very high, that means the current is stepped from, let's say, the cell is discharging a current of 3 ampere, suddenly it has to discharge a current of 10 amperes. So there is a sudden steep rise in the need of current or discharge of current. During those things, the cell may, you can say, it may be damaged because of resistance that is offered during the flow of the cells, during the flow of the current. During the flow of the current. So that has to be maintained. That means the need of current, or you can say the spike in current, has to be provided by some external source. Then slowly that has to be transferred to the cells. That means the cell will not be discharging from 3 ampere to 10 ampere directly. Rather, but there is a need, you can say, the vehicles has their need, you can say have their need that yes, it has to be, you can say at a given situation, I need 10 ampere. At a given situation, I need 3 ampere. And the situation shift in time, or you can say the time that is required in order to shift the situation is very low. So how to control all these things? What are the circuits that has to be used, or that has to be controlled by the BMS, or that has to be additionally installed to maintain the functionality of the BMS? Those things we'll be discussing in the upcoming sessions. So that, and you can say the working of all these things are all directed towards reaching these 3 objectives. Then charging control. First is discharging control. That means during discharge, the BMS should always monitor the discharging current and potential of the cells in order to maintain the optimal working region of the cells. Then charging control. Batteries are more frequently damaged by inappropriate charging than, I can say that, by any other cause. The main thing is charging, because we know batteries are spontaneous during discharge. The same has to be maintained during charge also. Batteries are very spontaneous, or cells are very spontaneous during discharge. So discharge can be managed properly. But again, to reverse the same reaction, we need charging. Charging has to force apart the reaction, or you can say has to cause the reaction. Though nowadays batteries are also spontaneous during charging, but still resistance is always there in charging, because we have to maintain a gradient. That means the charging current, or you can say the charging spontaneity should be less than the discharging spontaneity. That is what a property of a battery, that maintains the energy gradient. For that reason, we can say whenever we try to charge a battery, the battery is more frequently damaged by charging only, because we are forcing things inside the batteries. Therefore, charging control is an essential feature of the BMS. For lithium-ion batteries, a 2-stage charging method called the constant current and constant voltage charging method are used. So, what is this constant current and constant voltage method? We will be discussing. During the first charging stage, the constant current stage, the charger produces a constant current that increases the battery voltage. That means initially, if the battery is discharged, then a constant current is fed to the battery by changing the potential. Why do we need to change the potential? It is because the batteries, you can say when they are discharged, they will behave as a open circuit. That means you can say they will behave nearly as a resistance circuit. So, in order to, if we change the current too much, then the resistance increases. As I have said, that inside a battery, if the current changes are too high, then there is lot of resistance offered inside the battery or cells. So, if we change the current during initial phase of charging, then a lot of resistance will be there, lot of heat will be generated, batteries cannot be charged properly or within a given amount of time. Hence, constant current is fed. Current is not fluctuated at all, but the battery voltage is fluctuating. We all know what is a current and what is a voltage. Current means the amount of electron that is flowing through a given region. Voltage means at what rate the electrons are flowing. So, we control the rate of flow by keeping the amount of flow constant, so that there will be no resistance. When the battery voltage reaches a constant value, the battery becomes nearly full, it enters the constant voltage stage. You can say when the batteries are nearly full, then again you can say pushing a lot of current or lot of charge inside the battery becomes very difficult. So, now the current has to be maintained or it has to be fluctuated depending on the requirement by keeping the voltage constant. Because when the battery is near full, then you can say we cannot force any more charge inside the battery. Though we can do it, we are doing that through charging only. But what happens when the battery is full, When we force a lot of charge inside the battery, at that situation, it offers a lot of resistance. Same thing, again the battery thermal runaway can occur, the battery temperature may rise because of these things. Because of resistance is there, energy is being used, and the resistance that is offered because of the, you can say the, when the energy is being resisted. So it will be dissipating itself in various other ways. It will be dissipating itself as heat, as expanding, or you can say changing the state of the, you can say your substances or compounds and substances or elements that are used inside the battery. That means the energy has to be utilized. The energy cannot be kept because there is a constant flow of energy. So the energy is getting dissipated through heat, through change of state and all those things, and that may damage the battery. Hence, what we have to do, when the battery is near full, the potential is kept constant. That means the energy gradient. What is potential? It is nothing but the energy gradient. The energy gradient is kept constant so that the energy will not be lost in any other form. Then the current is maintained. The current is slowly, small amount of current, again sometimes large amount of current. It is maintained during the constant voltage stage at the near full region. At this stage, the charger maintains the constant voltage as the battery currents decays exponentially until the battery finishes the charging. The battery charging and discharging are not linear, though it is linearly shown in here, but nearly these are not, or you can say accurately, these are not linear. This is the graph for a constant current charging. You can say this is the region for constant current charging. Then slowly the current decays. That means the current slowly decreases. And this is the region of the constant voltage charging. That means voltage is maintained constant and the current slowly decays, so that the battery can be fully charged without degrading the life of the battery. Then state of charge determination. What is the state of charge of a battery? State of charge of a battery means the current reading of the battery or the current capacity of the battery. In your mobile phones, you have a battery bar. The battery bar shows the state of charge of the battery. That means what is the capacity of charge left in the battery. That is the state of charge of the battery. State of charge of the battery is nothing but a battery reading that shows us how much amount of work is, or how much amount of energy is left in the battery, or what is the capacity of the battery at a current state. That is the state of charge. One feature of the BMS is to keep track of the state of charge of the battery. The state of charge could signal the user and control the charging and discharging process. There are three methods of determining the state of charge. What are the three methods of determining the state of charge? Those are through direct measurement. That means when we measure the battery, so the battery will provide us with a battery potential. When we measure a battery, directly we don't go for current, because current depends on the resistance or the load that is provided to the battery. But the potential is, it is not independent of the load, I am not saying, but the potential is a direct measurement that can be taken from a battery. Then Coulomb counting. Coulomb counting means the amount of charge that flows to a battery, amount of charge that flows out of the battery. By counting all those things, we can determine the state of charge. Coulomb counting means during charging of the battery, we have counted how much coulomb of charge has entered the battery. And you can say when the battery discharges, then we count how much coulomb of charge has been taken out of the battery and how much coulomb of charge is left in the battery. That is found out through Coulomb counting. Then by combining these two techniques, we get a very accurate reading of the state of charge of the battery. To measure the state of charge directly, one could simply use a voltmeter, because the battery voltage decreases more or less linearly during discharge cycle of the battery. So though we know that what is potential? Potential is nothing but, potential difference, it is nothing but the energy gradient between two charges. Energy gradient between two charges. We know V is equal to K Q by R. What is Q? Q is the charge, K is a constant, R is the distance between the two charges. So when the distance is too much, the potential is, when the distance is less, we can say we have a, very high potential. To measure the SOC directly, one could simply use a voltmeter because the battery voltage decreases more or less linearly during the discharge cycle of the battery. Why do the battery potential decreases? It is because we know that the power of a device, power flow of a device is equal to its potential difference and the current flowing through the device. Power is constant. Power is constant for a device. That means the energy that the power can deliver, the energy that the device can deliver, or the battery, in here where we can say considering a battery, the amount of energy that the battery can deliver at a given amount of time is nearly constant. It is not constant, that means the maximum power that the battery can deliver or maximum energy that the battery can deliver at a given amount of time is nearly constant. Hence, if the current in the battery increases, then the potential of the battery has to decrease in order to conserve the power flow of the device or the battery in here. This is the reason why the battery potential decreases more or less linearly during the discharge cycle of the battery. The Coulomb counting method, the current going into or coming out of the battery is integrated to produce the relative value of its charge. That means the summation or the integration. If there is a specific function that governs the flow of Coulomb, or you can say the force that governs the flow of charge, then that function can be integrated through a period of time or throughout a period of time to get the total reading of the reading for the Coulomb counting. Then the voltmeter could be used to monitor the battery voltage and calibrate the SOC when the actual charge approaches either end. The battery current should be integrated to determine the relative charge going into and coming out of the battery. Why this integration is used in here? It is because we have integrator circuits. In BMS, we have integrator circuits and integrator logics. Summation won't provide a correct value of these things. Rather, an integrator circuit or an integrator logic can provide the correct value of any continuously ongoing, you can say any continuous process through a period of time or through a period or within a period. Then state of health determination. What is state of health of the battery? As we know, what is state of charge of the battery? State of charge means the amount of charge that the battery has at a given period of time. In the same way, the state of health of the battery. Remember, state of health of the battery is a continuous reading actually. That means the state of health of the battery, it decreases. We cannot again increase the state of health of the battery. Sometimes battery priming, battery conditioning or cell conditioning are done in order to increase the state of health. But nearly you can say when the health of a battery is degrading, then in order to again rejuvenate the battery, it is a bit difficult. So state of health of a battery is a continuously declining process. So let us know what is state of health. State of health is a measurement that reflects the general condition of a battery and its ability to deliver the specified performance compared with a fresh battery. State of health needs some time in order to correctly determine the value. That means in order to correctly determine the value of state of health of a battery, we have to test the battery for some time. Though manufacturers test their cell and provide us with a specific value of state of health when we install those batteries or cell in our modules, so that we can input those values to our BMS. That is, the initial state of health of this battery is this 1. Initial state of health of the battery is 1 or 0.9. It can maximum decrease to 0.1. Any such parameters such as cell impedance or conductance that changes significantly with age could be used to indicate the state of health of the battery. With not age, this is age. could be used to indicate the state of health of the battery. In practice, the state of health could be estimated from a single measurement of either the cell impedance or the cell conductance. These two things are generally measured or monitored in order to find out the state of health of the battery. So, why do we call a cell impedance? It is because any cell is represented by using a resistor and a capacitor. The resistor shows the internal resistance of the cell and the capacitor shows the charge capacity of the cell. Hence, we use cell impedance. Because in capacitance, while measuring the resistance of a capacitor, we don't use resistance, we use impedance. So, by measuring the cell impedance and the cell conductance, we can find out the state of health of the battery. So, why do the state of health of a battery changes? It is because of the impurity of the electrolyte. With continuous use of the battery, the electrolytes and the electrodes, they get impure or they degrade themselves with continuous use. When the degradation has reached a certain value, then the resistance of the cell or the impedance of the cell increases. So, by measuring the impedance and conductance of the cell, we can very well know the state of health of the battery. Then the third function of the BMS, and it is one of all these functions that we have seen, all are important. In the same way, cell balancing is also very important functionality of the BMS. What is cell balancing? Cell balancing is very useful for users actually, so that they don't have to change the battery or change the cell when you can say it completely degrades. Let's say previously I have said that no two cells are similar, all the cells are different from each other. So, some of the cells state of health may decline very fast, very rapidly. Some of the cells state of health may decline, or you can say decline slowly. So, what will happen if these things, or you can say if these things are happening within the battery pack? How will the BMS control the efficiency of the battery? Through cell balancing. Cell balancing is a method of compensating weaker cells by equalizing the charge on all the cells in chain to extend the overall battery life. In chains of multi-cell batteries, small difference between the cells due to production tolerance or operating condition tends to be magnified with each charge discharge cycle. Production tolerance and operating, you can say, production tolerance generally induce impurities inside cell. Let's say whenever a company is manufacturing cells, then it is manufacturing cells in a batch. In a batch means it is creating all those electrolytes in a very large batch, and the electrolyte has impurities. So, some of the batteries will induce, or some of the batteries will have X amount of impurities, some of the other batteries will have Y amount of impurities. Though they are produced in a single batch, all of them will have different amount of impurities because of the production method, how the batteries are designed. The batteries are designed in a very, you can say, means you can say how the compounds and how the elements that are designed in order to create a cell, to maintain a very good tolerance of those design is very difficult. Hence, impurities and irregularities are always there in cells. Not only impurities, irregularities are also there. Irregularities means you can say the cell, or you can say the electrolyte, or the electrode thickness, the electrolytic homogeneity, or you can say the distribution of electrolyte throughout the cell. If it may be uniform, it may not be uniform sometimes. So, those things induce lot of, or you can say, impurity during the manufacturing of the cell. Hence, no two cells are similar. Some of the cells may decline very rapidly, some of the state of health of the cells may decline very rapidly, and some of the state of health of the cells may decline very slowly. So, how to balance these things? In a battery pack, you have nearly 7,000 cells. Let's say 100 cells, you can say the state of health of hundreds of, or you can say 100 cells are declining very rapidly. So, how will the BMS manage all the cells correctly to get the proper output or to get an efficient output from the battery pack through cell balancing. During charging, weak cells may be overstressed and become even weaker until they eventually fail, causing the battery to fail prematurely. If any of the cell is failing, it is completely failing, then the battery pack will be damaged, or it can say it will become useless if any of the cell is failing, because that will disconnect the circuit. The cell will become completely resistive. Though during certain loading condition there may not be any problem, but during any other type of loading condition there will be problem. Hence the battery pack can fail prematurely if any of the cell is failing. Hence the BMS has to maintain the balance between the weaker cells and the, you can say, good quality cells. To provide a dynamic solution to this problem while taking into account the age and operating conditions of the cells, the battery may incorporate one of the 3 cell balancing schemes to equalize the cells and prevent individual cells from becoming overstressed. So what are those things? Active balancing scheme, passive balancing scheme and charge shunting scheme. These are the 3 schemes that the BMS uses in order to go for the cell balancing of, or you can say in order to go for balancing of the cells. In active balancing, the charge from the stronger cell is removed and delivered to the weaker cell. That means all the batteries, you can say active balancing, all the batteries, they have a similar charge. This is active balancing. That means the charge from the weaker cells are transferred to the, the charge from the stronger cells are transferred to the weaker cells. Because the charge from the stronger cells are removed and delivered to the weaker cells. Though you can say now all the batteries can be maintained at a correct SOC. In passive balancing, this is a dissipative technique used to find the cells with highest charge in the pack as indicated by higher cell voltage. The excess energy is removed through a bypass resistor until the voltage or charge matches the voltage on the weaker cell. So in passive balancing, what we generally do, let's say this is the minimum amount of potential that the battery or the cell can hold in a given module. Let's say a module has 40 batteries or 40 cells. So one of the cell of the module has lower SOC capacity. Then all other cells should have to maintain the same SOC capacity to maintain the voltage correctly. So what will happen? All these excessive charges are, you can say, dissipated to the surrounding through heat or through any other work. Okay. The excess energy is removed through a bypass resistor until the voltage or charge matches the voltage on the weaker cell. That means this energy is completely exhausted, or it is completely transferred to the environment or discharged to the environment. We are not storing these energies, rather this energy is completely getting discharged, or it is completely transferred it is discharged. Okay. The third thing is, in charge shunting, the voltage on the cell would be labeled upward to rated voltage of a good cell. In charge shunting, what will happen? You can say any of the weaker cells potential will be increased in order to maintain when the rated voltage of the cell is reached, the current would bypass the fully charged cell to charge the weaker cell until they reach full voltage. So what is this charge shunting? The voltage on the cell would be labeled upward to the rated voltage of a good cell. That means all the cells that are there in the module, all of the voltage will be labeled upward to the rated voltage of a good cell. That means you can say, because we know that a battery, or you can say in a module, a good cells, or you can say the good quality cells, they will be recharging faster than the bad quality cells. So the good quality cells are recharged first, or you can say the potential of the good quality cells are reached first. Then those potential, or you can say when the rated voltage of the cell is reached, the current would bypass the fully charged cell to charge the weaker cells until they reach the full voltage. That means now the charge from the good quality cells will be transferred to the charge or will be transferred to the lower quality cells or weaker cells, so that they will be having the required amount of potential and charge. You can say these active cell balancing and charge shunting methods are energy conservation methods. That means the energy is conserved within the system. It is not dissipated outside of the system. But the passive balancing scheme is a non-conservative. That means it is not conserving the energy of the system, that it is dissipating the energy outside of the system. Then some other functions of BMS. Communication. The communication functions of a BMS may be provided through a data link used to monitor performance, log data, provide diagnosis or set system parameters. That means the communication function, the function communicates with all the electronic devices that are installed in your hybrid electric vehicle and also all the devices that are being controlled by those electronic systems. Then you can say the BMS communicates with all those systems to set correct parameters of working for the battery pack. The functions also be provided by a communication channel carrying system control signals. Generally a bus. A bus is there. Through that bus, the BMS, you can say, communicates with all the control systems or control signals that are there or that are used in order to control the total circuit of the electric vehicle. The choice of communication protocol is not determined by the battery, instead it is determined by the application of the battery. The communication protocol is not determined by the battery. Where the battery is used or what is the use of the battery, that means whether the battery will be used for driving, whether the battery will be used for air conditioning, whether the battery will be used for any audio system, running any audio system, depending on the application of the battery, the communication protocols are set by the BMS. The BMS used in electric vehicle must communicate with the upper vehicle controller and the motor controller to ensure proper operation of the vehicle. As I have said, that the BMS communicates with all the electronic devices, all the mechanical devices that are installed in the installed in the hybrid electric vehicle for proper and optimal working of the battery pack. So these are some of the objectives or all of the objectives and functions of BMS. We have seen what are the various objectives that the BMS try to reach and how or what are the functions that are involved or that are controlled by the BMS in order to reach these objectives. In the next session, we will see a fully developed BMS and what are the components of the BMS. That means whenever we design a BMS, what are the things that we include in the BMS so that the BMS can be used to properly control the battery pack on which it is installed or for which it is installed. We will be designing the BMS in MATLAB and Simulink. So I am ending the session in here. Thank you. Hello everyone and welcome back. In the previous session, we have seen what are the various objectives and functions that are available to the BMS in order to optimize the working of the or optimize the working performance of the individual cells in a battery pack. Today we will see how do we model a BMS. What are the components that we install inside the BMS so that the BMS can work towards achieving the required objectives. So this is a simple BMS that is developed in MATLAB's Simulink. We have two modules in here. There is a plant module and there is a BMS module. The plant module generally stores the information about the battery pack. How a battery is modeled, what are the various things that we have to install in a battery pack so that the batteries or the battery modules or the cells can be maintained properly or can work accordingly. Inside the BMS, we have the logics or we have the functions included so that the BMS can very well control the battery pack charging and discharging. So let me show you the battery pack module first. That is we call that as the plant module. In a control system, we generally differentiate the plant from the control unit by naming it as plant module. There is a control module that is shown in here by the name BMS ECU, and there is a control module, that is BMS ECU, and there is a plant module that is being controlled by the controller. So inside the plant module, that is our battery module, we have battery pack, pre-charger circuit, charger and load. So inside the battery pack, we have two types of battery packs. So this battery pack is specifically designed in BMS to work for two types of battery packs. One is a 1 module 6 cell battery pack, another is a 16 module 96 cell battery pack. The BMS is tested in this design, then the algorithms, control algorithms of the BMS are installed in the physical BMS circuit. So you can see in here we have two types of battery pack. First one is a battery pack with 1 module and each module has 6 cells. Another is a battery pack of 16 modules, same, each modules having 6 cells. So the first battery pack has total number, or you can say total of 6 cells, and the second module or second battery pack has a total of 96 cells. If I open the module, in module there are two things. There is a cell module and there is a cell monitoring unit. Remember, monitoring units are installed along with the modules. That means they will be sensing all the potentials, all the currents and the temperatures of the individual cells, and they will be sending all those informations to BMS. Let me open the cell modules. In the cell modules, we have 6 cells arranged in series. Cell 1, cell 2, cell 3, cell 4, cell 5 and cell 6. These cells are nothing but the blocks that are available in Simulink library. All the values are taken from the manufacturer. That means what is the BMS no load voltage, temperatures, various types of temperatures, temperature dependent, or you can say voltage dependency and current dependency on temperature, state of charge of the battery, AH rating, capacity of the battery and self-discharging modules of, you can say self-discharging properties of the battery. Dynamics of the batteries are there, that is charge dynamics, that means how will the charge enter and exit from the battery, polarization resistance and you can say SOC settings. All these things are provided by manufacturer and some of the battery providers or battery suppliers. I will go for OK. So all the batteries in here are connected in series. The batteries can transfer charge, voltage and temperature with each other. These batteries, you can see these two batteries, they are connected in series so they can charge, so that they can exchange charge as well as potential. They can also exchange temperature. There is a convective heat transfer module that is installed in series along with all the batteries. So the battery can exchange heat also with themselves or with each other. In here you can see the outermost battery is connected to the ambient. This is the conductive heat transfer module that controls the that governs the temperature of the first battery, that is connected to the ambient. And the last battery or the innermost battery, it is not connected to any dissipative source. Hence, there will be a very large thermal gradient between all these batteries. The topmost battery will have very less temperature, or it will have less temperature than the innermost batteries. All these things are sensors that are installed in order to monitor the temperature of the battery according to certain charging and discharging current. These are the cell modules that I have shown you. Then after we have cell monitoring units. Cell monitoring units has potential meters and diodes. We know why do we use diodes? So that we will not be getting any negative potential in here. We will only get a positive potential in here. So potentiometers are there in order to monitor the potential difference across the cells or cell terminals. Those are fed to the BMS. You can see some of the informations are directly fed to the BMS, some of the informations go to the pre-charger circuit. In the previous sessions, we have seen how we have to install pre-charger circuits in our battery pack to control the sudden spike of current in the battery pack. When we open or close the circuit of the battery pack, then there is always a sudden spike of current. There is always a sudden spike of current whenever we close the battery pack circuit. In order to prevent any damage to the battery pack by those spikes of current, we install pre-charger resistors in the circuit. There are two types of resistors that are installed in this circuit, in this pre-charger circuit. First one is a inverter resistor, another one is a charger resistor. So, what is this inverter resistor? When the battery pack will be charged by the energy recovery systems, then it will pass through the inverter circuit. There can be spikes in current from the energy recovery systems also because of change in dynamics of the mechanical system. Those things can also be prevented, or those currents can also be managed in order to prevent any damage to the battery pack by using the pre-charger resistor inverter resistor. And the charging currents during charging and discharging of the battery can be managed by the pre-charger resistor charger. Okay. See, whenever the connection is closed, either the battery will be starting, or either the battery will be going for a charge or it will go for a discharge. Remember, whenever the connection is closed, either the battery will go for a charge or a discharge. Hence, the pre-charger resistor charger will prevent all those things. The capacitors are connected in parallel to the battery in order to maintain a low pass filter. After that, we have charger load. There is a charger and there is a driver load. The BMS controls the charger. Remember, the charger is not a component of the BMS. When we install a charger or when we charge the battery from an external source, then the BMS controls the charging current. It does not control the charger. So, this charger module supplies the current to the battery pack through the BMS. And the BMS decides what should be the charging and what should be the charging current that needs to be withdrawn, and that will have to be withdrawn from the charger. This is an independent charger that is connected to the battery pack through the BMS. And there is a drive load also. During discharge of the battery, the drive load will be withdrawing power from the battery or energy from the battery through the BMS. This drive load is nothing but the driver load. That means whenever you will be driving your vehicle or hybrid electric vehicle, the amount of current that is required for a specific driving condition is maintained or it is defined in here. The requirement for charging currents and requirement for discharging currents in drive load are all defined in these two modules. Then let me come to the BMS ECU. This is the circuit of the BMS. Not circuit, this is the design, or you can say control system or system engineering that is done for the BMS. There are limit circuits that generally sets the limits of various controls. That means what should be the minimum cell voltage, minimum cell temperature, maximum cell temperature. Maximum cell voltage, minimum cell temperature and max cell temperature. There are certain limits. All these limits are controlled by tables that are provided by the suppliers or the manufacturers. All the limits are provided from the tables only. For a given charging current, what should be the potential, minimum potential, what should be the maximum potential. For a given charging current or discharging current, what should be the minimum temperature, what should be the maximum temperature, in order to prevent any failure of the battery. All those things are provided by the manufacturer or the supplier. Or we can also get all those things or all these informations by testing a battery. After setting up all the limits, then the values are provided to the state machine. What is the state machine? The state machine is a logic circuit, or it is a brain of the BMS. It controls all the logics. That means if the temperature is above a certain range, if the temperature is below a certain range, what should be the path or what should be the option that has to be used. If there is any change in voltage, what should be done? All the decisions are provided in this state machine, or actions for a certain situation are provided in this state machine. If there is a minimum, if the battery is reaching a maximum temperature, what should be the action? If the battery is reaching a maximum current limit, what should be the action? If the battery is reaching a maximum voltage limit, what should be the actions? All those things are provided in this state machine. Defining the state machine needs an extensive control or extensive knowledge on state flow, a module of the MATLAB. Diagram based design of logics, not statement based. In programming or in programming language, in any of the programming language like C, C++, Python, MATLAB also, or other types of programming language like Java that are available, we have to provide logics using statements. But in state machine or state flow, the logics are provided using diagrams. It is a very robust method of providing working logics or action logics for a given control system. Then we have SOC estimations. See, SOC is not estimated directly from the battery monitors or battery readings. SOC is estimated by determining the current, the potential and the Coulomb counting from the batteries. And the SOC estimation is done by the BMS only. BMS gets all those data, all those readings from the battery, and it calculates the SOC or current SOC of the battery. It is because the readings may sometimes provide us with faulty results, because a weak battery can also provide a potential difference. Let's say if I am using a 24 volt battery or 24 volt cell, then the weak cell will also provide me a potential difference of 24 volts. A strong cell will also provide me a potential difference of 24 volts. But whenever I discharge them, for a certain time, the weak voltage and the strong voltage, they work concurrently or they work without any problem. But when the temperature increases, the weak cell, you can say, discharges improperly than the strong cell. So there can be a faulty reading in SOC estimation or in SOC of the battery. Hence those things are completely governed by the BMS depending on certain logics. Then balancing logic. If any of the cell is getting weaker or if any of the cell is stronger than other cells, then balancing logics are implemented. As I have said, there are three types of balancing, but in here active balancing is used. In here active balancing is used in order to balance the charge. Now the BMS and battery pack is modeled. Now how to test whether the BMS and battery pack is working correctly or not? For that, a test harness module is developed. Inside this test harness module, you can see this BMS closed loop. If I double click, I will get the battery pack and plant model. Various types of testing methods are provided in here. Standard testing methods are available in order to test BMS and the battery pack. So those standard test methods are included in this test sequence variants. There are two types of test sequence variants. First one is a automatic test sequence variance. That means it will provide all those values automatically to the BMS. That means any driving or any discharging or charging current will be provided automatically. And then another one is a manual variant. That means the user can provide the required charging and discharging current, generally required for certain conditioning and priming of the battery pack. So let me go for a automatic test sequence. Let me go for double click. There are 3 test cases in here. First one is a normal driving and standby. Second one is a aggressive driving. Third one is a standby or continuous charging. First one is charging and discharging, normal. Second one is aggressive discharging. Third one is normal charging. I will go for aggressive discharging and click OK. In order to run the model, we go for simulation and we run it. The model will take some time to start depending on the performance of the system that you are using. The model will take some time to compile and to load to the memory. Okay, all the components are loaded. Now let us run the system. So when I run the system, there is a scope. The scope generally receives all the signals from the BMS and shows it to the user. You can see there are different scopes or different scope windows in here. The cell voltage, the cell temperature, SOC, pack current and the BMS state. You can see the BMS is now in a driving state. That means it is in a discharge state. So the SOC is decreasing and the temperatures of the battery are increasing. As I have said, there is a temperature gradient between the cells of the battery pack. And yes, we are using one module 6 cell battery pack in order to simulate this model. We are not using 16 cell, so 16 module 96 cell battery pack. We are using one module 6 cell battery pack. You can see there is continuous driving state for which there is decrease in cell voltage because of the requirement of pack current and because of decrease in SOC also, and how the SOC is decreasing. So this is a second test module, that is the aggressive riding module. Then let us go for first test sequence, that is our normal riding and standby. Let us see how the cell temperature is increasing and how the SOC is maintained and balancing commands are activated. You can see again the BMS is going for discharge state. That means there is driving load on the battery pack. That means the battery packs are continuously discharged through driving loads. Driving load means whenever you are riding your vehicle, then you will be providing some driving load to your battery pack. You can see after driving load there is a standby mode. Standby mode means you can say the charger, or you can say you are driving your electric vehicle, then you have stopped in order to connect the charger. So that is the standby reason in here. That is the standby reason in here. This reason is the standby reason. That means you are driving your vehicle, then you have stopped your vehicle in order to connect the charger. So during driving, you can see how the temperature are increasing. During standby, there is a small change in temperature or decrease in temperature, and then during charging, the temperature is very well maintained. During charging, the temperature is very well maintained. You can see a constant current and constant potential charging method. Constant current and constant potential charging method. You can see when there is constant current, the potential is changed. And when there is constant potential, the current is changing. So both of the methods are available or applicable in this BMS. There is certain balancing command also at the end. Thank you. Hello everyone and welcome back. In the previous session, we have studied about how to develop various functionality of the BMS and how to combine all the functionality so that the BMS can work correctly in order to maintain the cell performance. Now we know battery pack. Battery pack is used to provide energy to our electric vehicle, and you can say the primary source of energy for electric vehicle is battery pack. And the primary discharging device is the motor, because motor consumes most of the energy of the battery pack. Power controllers are, you can say, they only take something about 10 to 20% of the total energy. The drivetrain and the motor, they utilize most of the energy of the battery pack. Nearly 60 to 70% of the energy is consumed by the motor only. So we'll be studying about various types of motor that are used in our electric vehicle, hybrid electric vehicle. So what is a motor? A motor converts electrical energy that it gets from the battery into mechanical energy, which enables the vehicle to move. That means we supply electricity to the motor and the motor converts that electricity on the process of, or you can say using the physical phenomena of magnetostatics, and it converts that same electrical energy to mechanical energy using magnetostatics phenomena, which helps the vehicle to move. You can say it is also used as a generator during regenerative action, which sends energy back to the secondary energy sources. So what is the secondary energy sources? In our electric vehicle or hybrid electric vehicle, we have seen that the primary energy source are the battery pack and the secondary energy source are the supercapacitors that stores energy in a very short interval of time. If we supply energy directly to the primary storage device, then we have to maintain that energy, and the energy that is generated during regenerative action, that energy is not that you can say it is a very fluctuating energy, and those type of energies can be very well handled by the supercapacitors. Hence we use secondary energy sources in order to store the energy that is produced during the regenerative action. EVs can have different numbers of motors. The Toyota Prius has 1, the Acura NX has 3. The choice depends on the vehicle and the functions it provides. We can have various types of motor. One very big motor in order to drive the vehicle, or small 2 to 3 motors in order to drive the vehicle. The big motor will be driving the powertrain as well as the gearbox. It is generally connected at the front of the vehicle. And if we have 3 or 4 motors, then 2 of them will be connected in the front, 1 of them will be connected at the rear. Generally used for increasing or you can say increasing traction of the vehicle. The motor from EVs include high power, high torque, wide speed range, high efficiency, reliability, robustness, low noise, reasonable cost and small size. Generally the motors that are used in electric vehicles, they have a very high power supply. They can generate very high torque. They have a wide speed range of control. They are very efficient, reliable and robust also. With advance of power electronics and control system, different motor types emerge to meet the need of automotive sectors. So what are the various types of motors that are used in electric or hybrid electric vehicles? The first common type of motor is a brushed DC motor. Then we have permanent magnet brushless DC motor, permanent magnet synchronous motor, the commonly used induction motor, more advanced switched reluctance motor, synchronous reluctance motor, permanent magnet assisted synchronous reluctant motor and axial flux or ironless permanent magnet motor. So these 4 motors, you can say they are new motors, or you can say these type of motors are yet not standardized while using in any electric vehicle. Induction motors and permanent magnet synchronous motors are generally used in most of the electric as well as hybrid electric vehicles. So first let us know what is the working of a brushed DC motor. How do a brushed DC motor works? These motors are permanent magnets to make the stator, or you can see these motors uses permanent magnet to make the stator. Rotors are brushes to provide supply to the stator. Okay, rotors have brushes to provide supply to the stator. Advantages of this motor are the ability to provide maximum torque in low speed. This type of motor, they have some disadvantages also. What are their disadvantages? Their bulky construction, low efficiency, heat generated because of the brushes and associated drop in efficiencies. The heat is also difficult to remove as it is generated at the center. So these brushed DC motors, they have certain advantages. What are their advantages? Their advantage is they can provide very high amount of torque. It is because of the inertia of these motors. We can say the rotor of the motor is magnetized by supplying electricity, and the stator is generally a permanent magnet. The rotor is magnetized by using or by supplying electricity, and the stator is a permanent magnet. Hence, you can say, since we are rotating a body with very less amount of mass, the losses are also very low. But it also has a disadvantage. What is the disadvantage? Disadvantage is, you can say, since we are using brushes in here, brushes tends to wear out after certain period of working. If the motors are continuously working, then we have to maintain the brushes at certain interval, or else we can damage the motor. Or you can say, these brushes, if these brushes will be failing, then it can damage any process or ongoing process of a machine or any other thing to which the motor is connected to. So the motors has to be maintained at a certain interval. The brushes has to be replaced, and some of the other thing inside these motors, or you can say like the commutators, these also has to be maintained or replaced in a certain interval to maintain the working of the motor correctly, or to maintain efficient working of the motor. You can say, these motors, they have a very bulky construction. Why do these motors have a very bulky construction? It is because of the mount points of the brushes. The brushes, you can say, are held by, you can say, 2 or 3 mount points, and those mount points are very heavy. We can't remove those mount points from the motor, for which the construction of this motor is bit bulky. And also we have to use bearings, because the rotor is made out of solid cores, or you can say there are laminated plates or laminated cores, and on those cores we generally wound the copper wire. And if the motor is very heavy, then we have to include bearings also, for which this type of motors, you can say, they have a very bulky construction, low efficiency also. Why do they have low efficiency? It is because of most of the heat is dissipated, most of the energy is dissipated as heat of the brushes. When the brushes will be in friction with the commutators, so the energy is lost. If we are supplying 20 joule of energy, nearly 5 joules of energy will be lost because of heat. And the heat is produced at the core of this motor, because we are magnetizing the core. We are not magnetizing the stator. The stator is already magnetized because we are using permanent magnets. But the rotor has to be magnetized, for which the heat is generated at the core of this motor. And since there is an air gap between the core or between the rotor and the stator, the heat cannot be efficiently dissipated to the surrounding, for which there is an associated drop in efficiency of the motor. So overall working of this motor, we can say, if we use this type of motor in electric vehicle, then we will be suffering from lot of losses because of heat, because of friction, and there will be lot of noise also. And the brushes has to be maintained at a regular interval. That increases the cost of maintenance of the total product. Now the second type of motor is a permanent magnet brushless DC motor. It does not have any brushes. Why is that? It is because the stator is magnetized and the rotor is made out of permanent magnet. When the stator is magnetized, then we don't have to change any, you can say, magnetic field through mechanical action. We can change the magnetic field through electrical switching. We don't have to go for any mechanical rotating parts in order to switch the magnetic fields. The magnetic fields can be switched very easily by use of electrical switching. Hence, they are brushless. The rotor is made out of permanent magnet. These type of motors, they are very efficient. Why is that? Because we don't have to energize the rotor. Only we have to energize the stator. Already the rotor is energized. The rotor of this motor are made out of permanent magnet, mostly neodymium ferrite. The stator is provided by an alternating current supply from a DC source through an inverter. As it has no windings in the rotor, there is no rotor or copper loss, which makes it more efficient than induction motors. Permanent magnet BLDC motor are lighter, smaller, better at dissipating heat as it is generated at the stator, more reliable and also has more torque density and specific power. These type of motors, they have a very high torque density than brush DC motors. Though brush DC motors can supply a lot of torque, but their working RPM is very less. We can say we are getting a very high amount of torque at a RPM of only 800 to 900. But in permanent magnet brushless DC motor, we can get the same torque at a RPM of nearly 1100 to 1200. Though in motor, the torque RPM graph is bit linear, and now to control the torque and RPM of the motor, we have to induce certain types of controllers. We'll be discussing about those controllers in upcoming sessions. Because of its restrained field weakening ability, the constant power range is quite short. The torque also decreases with increased speed because of back EMF generated in the stator winding. We know that motors can also be used as a generator. And in motors, there is always a phase lag between the switchings of the magnetic field. Now, when there is a phase lag, during those lag periods, back EMF can reduce the performance of the motor. If the currents are continuously fed to the motor, then the back EMF will not be hampering that much. But since the currents are provided in a wave format or sinusoidal waves, trapezoidal waves, any type of format, there is always a phase lag. And that phase lag, during that phase lag, the EMF, the back EMF that is generated can hamper the working of the motor. And also, this type of motors, they suffer from field weakening ability. Field weakening means since we are using permanent magnets are magnetized by certain arrangement of electrons. Okay. Hence, when we tend to use these permanent magnets for a long period of time, for a very, you can say, long period, then what will happen is these electrons, they tend to change their arrangement inside the permanent magnet, for which the field of the permanent magnet weakens after certain period of application, for which this type of motors, they suffer from field weakening ability, or this type of motors, they have a field weakening ability. The third type of motor is a permanent magnet synchronous motor. These motors are one of the most advanced ones, capable of being operated at a range of speeds without the need of any gear system. This feature makes this motor more efficient, compact and very suitable for in-wheel application, as it is capable of providing high torque even at very low speeds. Permanent magnet synchronous motors with an outer rotor are possible to construct without the need of bearings or the rotor. These motors' only notable disadvantage also come during in-wheel operation, where there is a huge iron loss that is faced at high speed, making the system unstable. Flux leakage in the air gap are sinusoidal in nature, therefore these motors are controlled by sinusoidal voltage supplies and vector controls. So, then induction motor. Before all these things, let me say you something. How do a motor works? We have studied about various construction of the motor, how the motors are constructed, what is a stator, what is a rotor. Rotor is the rotating part of the motor. Stator is the static part of the motor, generally the casing of the motor. Then there are windings. The windings can be on the rotor, the windings can be on the stator. If the windings are on the rotor, then we have to use brushes in order to supply or switch the magnetic field. If the windings are on the stator, then we can magnetize the motor very easily, or we can control the motor very easily without the use of any brushes. Now let's see one thing. How do a motor works? How do the magnetic fields of the rotor and stator interact? Let's say this is the outer casing of the motor. This is the outer casing of the motor. Now the outer casing has poles. Let's say this is pole 1, this is pole 2 and this is pole 3. It has 3 poles. Let me name them. This is my pole A, This is my pole B, or let me just name them numerically. This is my pole 1, pole number 2 and pole number 3. Now depending on the supply of current through poles, the poles are magnetized. So let me magnetize pole 1 and 2. So if I will be magnetizing those things, I will be magnetizing pole 1 and pole 2. So now there will be a magnetic field between pole 1 and pole 2. Now this magnetic field is a stator magnetic field. That means this magnetic field belongs to stator. Now I have a rotor also. Rotor will have a magnetic field of its own. If the rotor is made out of a permanent magnet, then it has a certain magnetic field. If the rotor is made out of permanent magnet, then it has certain magnetic field. Let's say this is the magnetic field of the rotor. Now I can impose this magnetic field, or I can just move this magnetic field to this center point. Because the magnetic fields will be available. I have just drawn a single line to represent the magnetic field, but the magnetic field has a lot of flux. The flux will be, you can say, arranged throughout the motor, or you can say the flux are available throughout the motor. In the same way, let me just translate the magnetic field of the pole that is generated by pole 1 and 2 to the center. Now there is a angle between the stator magnetic field and the rotor magnetic field. Remember, this blue one is the rotor magnetic field. This yellow one is the stator magnetic field. Let me just draw it. This magnetic field is of rotor. The yellow magnetic field is for stator. Now from magnetism, we know that if two magnetic fields are perpendicular to each other, then there is, we can say, maximum amount of imbalance, or you can say, what I will be saying is, let's say if I want to generate some torque by some motion between magnetic fields, then if the magnetic fields are perpendicular to each other, then maximum torque is generated. If the magnetic fields are perpendicular to each other, then maximum torque is generated. If they are perpendicular to each other. If they are parallel to each other, then torque generation is 0. Torque generation is 0. Or you can say, since we know that any dynamic system always wants to be in a state of lowest energy. Any system, dynamic system or static system, anything, always wants to be in a state of its lowest energy. So if the magnetic fields are perpendicular to each other, then that is the state of highest energy. If the magnetic fields are parallel to each other, then that is the state of lowest energy. Hence, always magnetic fields try to align themselves with each other, or they want to be parallel to each other to have a minimum state of energy, or minimum energy state. If they are perpendicular to each other, then they will be having the maximum energy state or maximum state of energy. So in here, what the rotor will try to do? The rotor will try to align itself with the magnetic field of the stator. The rotor will try to align itself with the magnetic field of the stator. You can say there is an angle between the magnetic field of the rotor and the magnetic field of the stator. So it will try to align itself along with the magnetic field of the stator. So now there will be motion, you can say. The rotor will try to rotate in order to align itself to the magnetic field of the stator. Now when the rotor is aligning, or is aligning, in the process of aligning, before reaching, or you can say before complete alignment or before perfect alignment, the magnetic field will be switched in order to continue the motion, or else there will be what? There will be start-stop motion. Means whenever we supply some current, then there will be a sudden motion during alignment, and when it is aligned, there will be no motion. or the torque generation will become completely zero. We don't want that state in a rotating device. The rotating device should be rotating continuously. So in order to make the motor rotate continuously, we switch the magnetic field at certain interval. We never try to align the magnetic field of the rotor with the magnetic field of the stator. We always want to keep the magnetic fields perpendicular to each other. Not completely perpendicular, but there should be an angle where the torque generation, or you can say the amount of torque that is generated, can be utilized correctly. So now you can see the magnetic field is rotating in here. Now let me just erase this one. Now the magnetic field, you can say the rotor magnetic field will be arranged like this. It will be arranged like this, because it is trying to align itself with the magnetic field of the stator, the magnetic field that is produced by pole 1 and 2. Now the magnetic field is switched. Between poles 2 and 3. The magnetic field is switched between poles 2 and 3. If I just translate this magnetic field in here, you can see now I have another angle, and the angle is larger than 180 degree, sorry 120 degree. It's the angle. Since the rotor will have certain inertia, so it will try to rotate in this direction in order to arrange itself with the magnetic field of the stator. Again there will be certain rotational motion. Now again my rotor will try to arrange itself along with the magnetic field of the stator. Now again we are switching the magnetic field. We are switching the magnetic field between poles 1 and 3. Now if I just translate the magnetic field to the center, you can see now there is some angle between the rotor magnetic field and the stator magnetic field. Remember, the rotor magnetic field is generated by a permanent magnet. The stator magnetic field is generated by flow, or you can supplying current to the windings. So the poles magnetic field can be switched, but the rotor magnetic field is uniform. The rotor magnetic field is completely uniform because that is generated by a permanent magnet, while the magnetic field that is generated at the stator can be switched or can be controlled. The magnetic field intensity can be increased and also can be decreased. Direction can also be reversed or changed depending on the type of operation. Now again there will be a motion of the rotor in order to arrange itself along with the magnetic field of the stator. So this is how a motor rotates. By continuously varying the magnetic field at the stator or at the rotor, we create a continuous motion of the motor. This is how simple any permanent magnet, BLDC motor, any brushed DC motor works. Induction motor also works on this principle. But you can say the switched reluctance motor and the synchronous switched reluctance motor, they don't work on this principle. They work on a different principle. We'll be discussing about those principles. Before that, let us know the working or construction of an induction motor. Induction motors were used in early EVs like GM EV1 as well as current models like Tesla. Among the different commutator-less motor drive system, this is the most matured one. Vector control is useful to make IM drives capable of meeting the needs of electric vehicle system. Field-oriented control can make an induction motor act like a separately excited DC motor by decoupling its field control and torque control. Flux weakening can extend the speed range over the base speed while keeping the power constant. Field orientation control can achieve a range of 3 to 5 times the base speed with induction motors properly designed. Current EVs employ 3-phase 4-pole AC motor with copper rotors. Remember, the induction motor works on the principle of magnetic induction. The permanent magnet motors, you can say there is no induction. The rotor is already magnetized and the stator is magnetized by supplying current. But in induction motor, the rotor is not magnetized. The stator is only magnetized by supplying current. Then how is the rotor magnetized? The rotor is magnetized by induction. We know induction in our transformers. Like in transformers, there is a primary coil and there is a secondary coil. There is no direct connection between the primary coil and the secondary coil. Then how is the power transferred from one coil to another? Through the process of magnetic induction. In the same way, rotor gets magnetized in an induction motor. That means when we supply or when we generate magnetic field at the stator, that magnetic field magnetizes the copper bars that are installed in the rotor of the induction motor. Those copper bars gets magnetized and therefore they generate their own magnetic field. It is just like there is a ferric substance or there is iron and there is a magnetic bar. If we just bring this magnetic bar near the iron, then iron also gets some property of the magnetic bar. It is because of the flux linkage. In magnetic bar we have flux. So in the iron or soft iron core, I will be naming it as soft iron core, comes in contact with the flux of the magnetic bar, then the soft iron core also gets magnetized. When the iron bar is removed, again the soft iron core gets demagnetized. So the rotor of an induction motor can be magnetized and also can be demagnetized. This is the reason why the efficiency of the induction motor is bit less than the permanent magnet motor. Why is that? Because we have to provide additional energy to the stator, because the stator will be magnetizing the rotor and the rotor will be generating its own magnetic field depending on the arrangement of the copper bars. You can see in here there is a diagonal arrangement of the laminations. Why is that? It is because to prevent any stagnation. If the arrangement is completely straight or parallel to the axis of the rotor, then there can be a magnetic stagnation. Hence, in order to prevent any magnetic stagnation, certain skewness is provided to the lamination, so that the magnetic force on one side of the lamination and on the other side of the lamination will have a phase gap, for which there will be no stagnation. So remember, both of them will be reaching a force of 90. Let's say 90 Newton is the force on both of the sides. But if they are completely arranged, or you can see if the lamination is arranged parallel to the shaft, then both of the sides will have 90 Newton of load and they can reach a stagnation. But since there is some skewness, there will be certain phase lag. What is that lag? That lag is, since this 90 Newton, it is not reaching directly. It is reaching the 90, you can say the 90 Newton of load is reached through a certain cycle. So if one of the side has reached 90 Newtons, the other side will have less than 90 Newtons, let's say 80 Newtons. Now for this reason, there will be no magnetic stagnation. In order to prevent this type of stagnation, certain skewness is provided on the rotors. Remember, the rotors are made out of copper bars, laminations. Inside those laminations, we have copper bars. Laminations are made out of soft iron core. Now, there is another term in here, that is field orientation control. what is this field orientation control? In induction motors, the poles or the motor is divided into sectors. In induction motor, the you can say core or the stator is divided into sectors. What are those sectors? Let me draw. Let's say this is the casing of my induction motor. Now it has 4 poles. Let me just draw the poles. Pole number 1, pole number 2, pole number 3 and pole number 4. Now all these poles, they have certain sectors. What are those sectors? Let me just draw those sectors. This is sector 1. Sorry, let me just name the sectors. Sector number 1, sector number 2, sector number 3 and sector number 4. Sector number 1, sector number 2, sector number 3 and sector number 4. Now we have two types of magnetic field. There will be a stator magnetic field and there will be a rotor magnetic field. Yes or no? There will be a stator magnetic field and there will be a rotor magnetic field. In permanent magnet, there are also sectors, but there is no specific field orientation control. That means there is no logic that will be controlling the field orientation. But in induction motor, there is a specified logic in order to control the field orientation. How is that? Let's see. This is the magnetic field, sorry. This is the magnetic field of my stator. In the same way, I will have a magnetic field of my rotor. Let's say this is the magnetic field of my rotor. Let me just name them. This is my rotor magnetic field and this yellow one is my stator magnetic field. Now we know that the rotor magnetic field follows the stator magnetic field in order to align itself. Now there is certain angle in between the stator magnetic field and the rotor magnetic field, and the rotor wants to overcome this angle, or it wants to decrease this angle. So the rotor will start rotating. Now when the rotor reaches a certain sector, let's say this is rotor is at sector 2, you can say stator magnetic field is at sector 1, rotor magnetic field is at sector 2 and the stator magnetic field is at sector 1. So now when the rotor will reach near the sector 2 or near the end of the sector 2, that means it is just entering sector 1 and it is leaving sector 2. The rotor magnetic field has just reached this location. It will just exit the sector 2 and it will just enter the sector 1. At that point, what happens? The stator magnetic field is also changed from sector 1 to sector 4. Now let me again draw those things. The rotor magnetic field has reached near sector 2 or at the end of sector 2. That means it will be exiting the sector 2 and it will be entering the sector 1. Now before entering the sector 1, what is, you can say, the field orientation controller will change the location of the magnetic field of the stator. It will just shift the magnetic field to sector 4 when the magnetic field of the rotor reaches near the end of stator 2. Now again there is certain angle. Between the stator and the rotor. So now again the rotor will try to catch the magnetic field of the stator, and when it reaches near the end of sector 1 and it will just be entering the sector 4, again the magnetic field of the stator is switched. Let's say again, let me draw it. Okay. Now, when the rotor's magnetic field will reach near the end of, or it will try to exit the sector 1 and it will try to enter the sector 4, the magnetic field of the stator is switched again to sector 3. So, this is what is a field orientation control. This is what is a field orientation control. That means the magnetic or the motor is completely divided into sectors, and depending on the position of the magnetic field of the rotor, the magnetic field of the stator is switched in order to maintain this sector balance, so that the torque that is generated will always be constant. There will be certain ripple in the torque, but that ripple is constant. It is because we have just divided the motor into various sectors and we are monitoring the, you can say, rotation of the magnetic field of the rotor. So, we can very well switch the magnetic field of the stator. We are not just taking into account the supply phase. That means, if the phase is supplied at a certain frequency, then that frequency will switch the magnetic field. So, the switching of the magnetic field is completely dependent on the supply in motors that does not have any field orientation control. Sometimes the supply can fluctuate, so the switching will also fluctuate. But in motors that has field orientation control, the switching is very accurate. Even if the supply is fluctuating, the switching is very accurate. So that helps us to maintain the power supply of the motor, to maintain both torque and RPM of the motor also. So this is the field orientation control of the motor. Generally, the magnetic field of the rotor or the magnetic field of the rotor is generally sensed by using certain sensors, or we call those sensors as Hall sensors. Hall sensors generally monitor the RPM of the rotor, and also certain sensors are there, magnetic sensors are there, that also senses the rotating magnetic field of the rotor, and they provide us with a very accurate placing of the magnetic fields of the rotor and stator, so that the switching can be done very efficiently without including any type of switching from the power supply. So this is the field orientation control that is used in induction motor in order to decouple its torque control from its field control. That means, if the field is controlled by the power supply, then torque is also controlled by the power supply. But in field orientation control, it is decoupled. Even if the field control is controlled by the power supply, the torque control is completely controlled by the field orientation control. This is how an induction motor works, or the field orientation control of an induction motor works. Then we have the most advanced motor, that is a switched reluctance motor. Switched reluctance motor, also known as a double salient motor, because of having salient poles both in stator and rotor. These are synchronous motor driven by unipolar inverter generated current. They demonstrate simple and robust mechanical construction, low cost, high speed, less chance of hazards, long constant power range and high power density, useful for EV application. Permanent magnet is not required for such motors, and the facilities enhanced reliability along with fault tolerance. Permanent magnet are not required for such motors, and that facilitates enhanced reliability along with fault tolerance. On the downside, they are very noisy because of variable torque nature, have low efficiency and are larger in size and weight when compared to permanent magnet machines. Then we have switched reluctance motor, synchronous switched reluctance motor or synchronous reluctance motor. A synchronous reluctance motor runs at a synchronous speed while combining the advantage of both permanent magnet and induction motor. They are both robust and fault tolerant like induction motor, efficient and small like permanent magnet motor, and don't have drawback of permanent magnet systems. They have a control strategy similar to that of a permanent magnet motor. The problem with synchronous reluctance motor are associated with controllability, manufacturing and low power factor which hinders its use in EVs. However, research has been going on and some process is made as well, the main area of concern being the rotor design. One way to improve is by increasing the saliency which provides a high power factor. Just see the rotor design. Why are these rotor designed in such a way? Why are these rotor designed in such a way? There is no winding. Then why are these rotor designed in such a way? Okay, let's see first how a synchronous motor works. How a synchronous motor works. So for that we have to know how magnetic field is generated by any substance. Let's say I have a soft iron core. I have a soft iron core. Now the soft iron core has various regions. It has various regions inside it. So when a soft iron core is not magnetized, then all the electrons are arranged in random state or random direction. The electrons are arranged in random direction. Let me just copy it. All the electrons are arranged in random direction. There is no such particular direction in which the electrons are arranged. So in the soft iron core is not. So when the soft iron core is not magnetized, then all the electrons are arranged randomly. That means the magnetic field of the electrons are arranged randomly. We know electrons are small magnets. Why do electrons have magnetic property? No one knows. That is a fundamental property of the electron. You can say that is a fundamental property of the electron. No one knows why they have magnetic field. But they behave in a certain way when they are exposed to certain magnetic field. So you can say in here the electrons are completely, or you can say they are randomly arranged when the permanent magnet, when the soft iron core is not magnetized. Completely random arrangement of electrons. Now, if we bring a magnetic or if a magnetic bar near the soft iron core, what will happen? Let's say if we bring a magnetic bar near a soft iron core, a north pole and a south pole. Now, This magnetic bar has flux. Now this flux will also flow through this soft iron core. Now when the electrons come under the influence of this flux, then they arrange in a particular direction. They arrange themselves in a particular direction. That increases the magnetic effectiveness of the system or of the soft iron core, or the soft iron core becomes magnetized. That's all. When the electrons are arranged in certain way, the soft iron core become magnetized. Because in electron we have a south pole and a north pole also. Remember, in electron we have a south pole and north pole. So when the electrons are directed along a certain direction, then any one of the pole gets, or you can say the poles gets arranged. You can see now they are arranged in a certain direction. The amount of resistance that this soft iron core will provide is known as the reluctance of the soft iron core. The amount of resistance that this soft iron core will provide, that is the reluctance of the soft iron core. The switched reluctance motor work on this principle only. It works on this principle only. In induction motor, in permanent magnet, BLDC motor, the rotor magnetic field will follow the magnetic field of the stator. They will never catch each other, but there will always be a chase between the rotor magnetic field and the stator magnetic field. But that is not the case in switched reluctance motor. Why is that? In switched reluctance motor, the rotor is a part of the stator's magnetic field. Let's say this is the rotor made out of soft iron core. This is the rotor made out of soft iron core. Then the rotor is a part of the stator's magnetic field. This is the magnetic field of the stator. It will completely pass through the rotor. And when the stator magnetic field is rotated, then the rotor will also rotate along with the stator's magnetic field. The rotor will rotate along with the stator's magnetic field. Okay. The rotor will rotate along with the stator's magnetic field. Let's say this is 0 degree, this is 180 degree, then I have 360 degree. That means the rotor is a part of the stator's magnetic field. The rotor is a part of the stator's magnetic field. And the rotor will rotate along with the stator's magnetic field. That means when the stator magnetic field will rotate, the rotor will rotate along with it. When the stator's magnetic field will rotate, the rotor will rotate along with its magnetic field. This is how a switched reluctance motor works. Okay, this is how a switched reluctance motor works. The magnetic field of the switched reluctance motor, we can say, are linked with each other. That means the rotor magnetic field is similar to the stator magnetic field. When the rotor magnetic field will rotate, when the stator magnetic field will rotate, the rotor magnetic field will also rotate along with it. Okay. So this is how a switched reluctance motor works. So there will be certain lag also. If you ask, sir, the rotor do have some inertia. The magnetic fields, they don't have any inertia. The magnetic field can rotate without any resistance, because the magnetic field, they don't have any mass or they don't have any inertia. But the rotor has some inertia. Yes, the rotor has some inertia. Hence, when the rotor will be rotating with the magnetic field of the stator, there will be certain gap or lag. The rotor will not align itself completely with the magnetic field of the stator. There will be certain lag. So for that, you can say purpose only, the rotors are made very light, or the construction of the rotor is very light. The construction of the rotor is very light in order to reduce the inertial losses by the rotor. Okay, there will be always some lag between the rotor and the stator, but that lag is constant. But sometimes the lag also increases with increase in RPM. In order to capture the working of this switch reluctance motor, what we generally do? We generally reduce the mass of the rotor and increase the magnetic efficiency of the stator. We reduce the mass of the rotor and we increase the magnetic efficiency of the stator. Okay, so I'll be ending the session in here. In this session, we have studied about various types of motors, the construction and working of various types of motors, and which type of motors are very suitable for EV applications also. In the next session, we'll study about various types of powertrains that are available for electric vehicle and the vehicle dynamics. Thank you. Hello everyone and welcome back. In this session, we will learn how we can design a simple motor in RMS expert module of ANSYS electronic desktop. We will be following some reference from this paper, Performance Analysis of Induction Motor using ANSYS. Some of the values that are required in order to model a motor are provided in here. We will be using these values. Some of the values are not in here, so I will be providing those values myself and will be generating the result that is there in this paper. So let's start the modeling. For that, you have to install ANSYS electronic desktop. You can download ANSYS electronic desktop directly from the ANSYS website. For students, ANSYS electronic desktop is free. For professionals, you have to download the ANSYS electronic desktop using subscription. So the project one is already created. Whenever you will be opening the ANSYS electronic desktop, a default project gets created. So this project is already available in here. So what we have to do is we have to add certain definition to this project. So for that, we have to go for Maxwell. In Maxwell, we have RM Expert. Click on RM Expert. Then select the type of motor that you want to design. In here, you have two types of wizard. Maxwell Model Wizard and RM Expert Solutions Wizard or Solutions tab. Just select this Generate RM Expert Solutions and select the standard models. We'll be creating a 3-phase induction motor in RM Expert. So select the 3-phase induction motor and click OK. The design module for designing the 3-phase induction motor is now loaded. So what we have to do is we have to provide some of the parameters that are required in order to design the motor. So first we will be providing the default parameters of the motor. Before that, we also have to provide what is the working condition or what is the working parameters of the motor or working environmental parameters of the motor. For that, we have to go for RM Expert, and in here you have an analysis setup and go for add solution setup. In solution setup, we will be providing some of the working parameters of the motor. So what is the rated output power? Let us refer to the paper. In here, you can see the rated output power of the motor is 1100 watt. The rated voltage is 330 volt with a reference speed of or rated speed of 1450. So let us use these values. So I will be going for 1100 watt. Rated voltage is 330, rated speed is 1450. Operating temperature is 75. Since this is a 3-phase induction motor, we have to provide the working frequency. So I will be going for 50 Hz, that is the general working frequency for any type of induction motor, and the winding connection that we will be using. There are two types of winding connection. One is a delta winding, another is a wave winding. We will be using the wave winding connection. I will go for OK. Now we have to define the design parameters for our machine. Number of poles. This machine has two poles. It is a 2-pole induction motor. We will be getting those values from here. Number of poles is 2, stray loss factor is 0.01, frictional losses is 0 and windage losses is also 0. These frictional losses and windage losses are not considered in this modeling. Reference speed 1450. I will go for OK. So my machine parameters are set. After that, I will go for my stator parameters. So what is the outside diameter of the stator? Let me again refer to these values. Outside diameter is 140, inside diameter is inner diameter is 78 and length is 250. So 140, inner diameter is 78 and length is 250. Stacking factor, that means the ratio between the laminated core to the solid core. That means if the core is solid, then what is the total surface area? And if the core is laminated, what will be the total surface area? The ratio between the laminated core to the solid core is the stacking factor. It is 0.95. Steel type is D21_50. So stacking factor is already provided in here. This is the default stacking factor we consider while designing any type of motor. Steel type, let me go for selecting the steel type. The steel type that we will be using is a magnetic steel, or it has certain magnetic parameters, generally a soft iron core steel. So I will be going for D2150. It is already available. Select this steel, then go for OK. You can also view or edit the material properties of this steel. I will go for OK, I will go for OK, and I will go for OK. So the steel is selected. Number of slots 36. We are using 36 slots on which the windings will be done. Slot type is 1. There are various types of slot types are available depending on the type of application of your motor. Since we are designing a simple induction motor, I will be going for slot 1. Okay. Lamination sectors 3. I have 3 lamination sectors. Pressboard thickness, I don't need any pressboard thickness nor any skew width. Then OK. You can see this is the outer diameter and this is the inner diameter of my stator. Then in stator there are other 2 parameters, that is slot. So I have to provide the dimension of these parameters of slot. So for that, double click and slot parameters are available. So auto design is switched on. That means ANSYS will be providing us some of the recommended values for the parameters that are not given in here. I will switch off the auto design and I will go for providing the parameters of my own. Switch off the auto design, go for apply, OK. Again click on the slot. You can see the parameters are available now. So what are the parameters that we will be using? Let's see. Induction motor rotor slot. So rotor slots parameters are provided in here. Rotor slots parameters are provided in here. I have to design the parameters for a stator. Means I have to provide the parameters for the slot of a stator. Hence, those things are not provided in that paper. In some other paper, those are provided. So I will be using those values. This is 2, HS0. You can see, you can refer the diagram in order to find out the values that I am providing. HS0 is 15. BS0 is 1 and BS1 is 5. BS2 is also 5. I will go for OK. After slots, I will be providing the dimension for the windings. The winding dimensions are also provided in the paper. Let me provide those dimensions. Winding layer, I will be using a single layer winding. I will not go for multiple layers or more than one layer of winding. Then whole coil, I will be using a whole coil. You can see whole coil and half coil, there are 2 types of winding arrangements. I will be going for a whole coil winding. Parallel branches for windings is 1. Conductors per slot is 30. Number of conductors per slot, that means the number of windings per slot is 30. Number of strands I will be using 1. Wire size, I will not be using any coil pitch, nor I will be using any wire wrap. I will be going for providing the diameter of my coil that I will be using for winding. The diameter is 21.5. Sorry, the gauge number is 21.5. That has a diameter of 0.683. I will go for OK. Now end insulations. What are the end insulations that I will be providing in my winding? So half ton length, yes, I want half ton length. Base inner radius, I will be providing the value 10. Tip inner diameter, I will be providing 2. End clearance is 1 mm. Slot liner is 1 mm. Waste thickness is 1 mm. I will not be using any layer insulation. That means there is no insulation between layers. Limited fill factor is 0.25. I will be using these values and I will be going for apply and then I have to define the parameters of the rotor. The rotor parameters again I will be defining from here. Stacking factor is 0.95, number of slots is 28, slot type is 1, outer diameter 76, inner diameter 32. Stacking factor is 0.95, number of slots is 1. Sorry, number of slots is 28. Slot type is 1, outer diameter is 76. The inner diameter of the stator was 78. So there is a 1 mm of air gap between the rotor and the stator. Inner diameter is 32. Length is 250. The steel type that I will be using in here, I will be using the same steel type, that is D 2150. So D 2150. Okay. It is saying that already this material is assigned, so you can directly use the material from that assignment also. Then skew width. Do I need any skew? Yes, skewness is required. I will go for 1 because we are discussing about the skewness in our induction motor. So I will be providing a skew width of 1. Will this be a cast rotor? Yes, this will be a cast rotor. Cast rotor has very good magnetic property. I will go for OK. Apply. You can see if I click on the machine, I have my stator and also I have my rotor. Now I have to use or I have to provide rotor slots and rotor windings. So slot diameter of the rotor, it is already provided in here. 228345. Okay. I will be providing 228345. Okay. Slot dimensions are provided. Now I will be going for windings. Since this is an induction motor, so I am using copper as my windings. I have said that in induction motor, the rotor is completely made out of copper bars and laminated slots. So what are the length of the copper bars that I will be using? And what is the material? Material is same D21. Sorry, material is same copper. Because I am using copper bar. Copper. Okay. Edge length is 5. That means the edge length of the copper. The ring width that the copper is installed to is also 5 and the ring height is also 5. And end ring connection is also made out of copper. I'll go for OK. Now OK. So my rotor and slots are all done. Then I'll go for shaft. I'll be selecting the magnetic shaft, then OK. So once you have provided all those values, now it's time for validating the values. That means whether the values that I have provided are correct or not. So I'll go for RM expert and validation check. You can see all the values that I have provided are validated or they are all correct. Now after validation, I'll go for analyze all those values. I'll go for analyze all. So it is asking to save the induction motor. I'll save the induction motor as batch 7. Then my analysis will start in here. After the analysis is done, I will go for the message manager. In message manager, it is saying normal completion of the simulation on server. That means there is no problem in my simulation. So after the analysis is complete, then I will just right click and I will create a Maxwell design. I will create a 2D Maxwell design. Then I will go for OK. The Maxwell will automatically create the motor that I want by using the values that I have provided. You can see the design process is completely automatic. Though I can also create this type of motor using the parameters that are provided in here, or using the features, design features that are provided in here. But since I have already provided the parameters, ANSYS Maxwell will create the design by using those parameters. But I can design any type of motor, any type of slot by using the features, design features that are provided in here. You can see my design is complete. Now once you have imported or once you have completed a design, then again you have to go for a validation check, so that ANSYS has used all the parameters correctly in order to create this design. ANSYS has created or used all the parameters correctly in order to create this design. So I will go for Maxwell 2D and validation check. There is some problem in boundaries and excitations. How can I know what is the problem? ANSYS is showing me that there is some problem in boundaries and excitations. But how to know what is the problem? Boundaries we can have a lot of boundary conditions, a lot of excitations are available. How to know what type of boundary condition and what type of excitation problem is there? For that, I will be visiting my message manager. In message manager, you can see there is a warning sign, AD effect settings may need a revisiting due to recent change in the design. The default value will be used for the object if the value is not specified. So ANSYS is saying me that there needs to be some change in the AD effects. So how to do that? Go for edit and select all. All the components of the motor are selected. Since AD losses is applicable for all the components, so I will be selecting all the components, right click, assign excitation. So in the excitation, there is a set AD effects. So I will be setting AD effects for all the bars that I have created. Why is that? Because bars, the surface area of the bar or the volume of the bar is very large as compared to the coils. So the bars will have very high amount of AD loss as compared to the coils. The coils will have very negligible amount of AD loss. So I will select all the bars of the rotor, then I will go for OK. Now again, if I go for Maxwell and validation check, you can see there is no problem in here. So now I am ready to create the simulation. Okay. In order to create the simulation or in order to create the analysis, first I have to set up the analysis type. So I will go for, you can say an add solution setup. In add solution setup, there are some default timings in here. These are all in nanoseconds. If I just convert it to seconds, I will be using a stop time of 0.01 second with a time step of 0.001. With a time step of, I will be going for 0.2 seconds, so that I can have a very long simulation for animation. Then save fields, custom. I want to have a custom save field. You can say sometimes the custom save field is not available. So click on every and again click on custom. So already the save fields are available. All the settings will be default. Save fields means the results of the simulation will be saved so that I can create an animation from the results. So I will go for OK. Again, let me see the analysis setup that I have created. Let me see the total number of time steps that are created in analysis setup 2. Save fields, you can say preview. I have 20 time steps. Close. OK. Now since I am in Maxwell design, I don't need any RM expert parameters. Then again I will go for validation check to see whether the time step that I provided are working correctly or not. Okay, these are working correctly. Then I need to see some results. Okay, I need to see some results. So I will be providing certain results to see. How to do that? You can see I will be going for edit, select all, then Maxwell 2D, result, fields. I want to see flux lines on all objects. Done. In field relay, you can see my flux lines are already there. Again, I will go for edit, select all, Maxwell 2D, fields. I want to see the magnetic intensity also, magnetic H and magnetic B for stator and rotor on all objects. Done. Then again edit, select all, Maxwell 2D, fields and magnetic B also on all object. Okay, done. Then again edit, select all, Maxwell 2D, fields. I want to see the energy losses and energy utilized in my motor. Again edit, select all. I also want to see the losses. I want to see the ohmic losses and temperature of my motor. So I'll go for edit, again select all, Maxwell 2D, fields, temperature on all object. I'll go for OK. So all the fields that I want to see are done. Then what I have to do? I have to go for plotting the results. So in order to plot, I'll go for fields. In order to plot, I'll go for results, create transient plot, rectangular plot. So what are the things that I want to see in the plot? I want to see windings. In windings, I'll select the induced voltage and the induced currents of all the phases. Then I'll create a new report. Then close. And once this is done, I'll go for Maxwell 2D and analyze all. My analysis will take some time to complete. I want to see the progress of my analysis. So I'll click on this, show progress. You can see my simulation is starting. I will be needing nearly 20 time steps. You can see the induced voltage and induced currents. They will be following a sinusoidal pattern with certain phase difference. You can see the up and downs in the curve. It is only because of the losses that the motor is experiencing. The eddy losses and the core losses and the resistance losses. Okay, the solution is done. Now we can see the results. You can see there is a lot of fluctuations in the solution. It is only because of the losses that we have included in our simulation. The eddy losses and some of the stray losses and winding losses are ignored, but the eddy losses is included. Since the eddy losses is included, the core losses and there will be some solid losses. There will be some core losses as well as there will be some solid losses. So these are the, you can say, induced voltage at phase A, phase B, phase C, because this is a 3-phase induction motor. We have created a 3-phase induction motor. You can see there is phase lag between various phases. This is how current is supplied to the motor. And with this supply of current, we are getting this torque. This is the torque that we are getting, torque output of the motor. And we have certain losses in the motor also. This is the solid loss. Solid loss means, since we are using a solid loss is nothing but it is also a type of eddy loss. Solid loss is nothing but it is type of AD loss, and also we have solid loss because of temperature. Because temperature, you can say the amount of energy that we are providing to the motor. Some of the energy is also lost through temperature, friction, AD losses. So out of all these losses, solid loss consists of AD as well as temperature. This is the position. You can say in this way, the motor is transiting. This way the motor is transiting. And we have some solid losses again at the end connection. What is the end connection? You can say this is the solid losses at my stator. Okay, this solid loss plot 2, the solid losses at my stator. The same type of solid loss also I have my rotor, at the end of my rotor. Because ring connection and end connection we are providing for the rotor. These are the various types of losses that I have for my rotor. Now, if I want to see some of the results, you can say these are the results that we have selected so that we can analyze these results. So, how to analyze these results? Nothing, just double click in here. The motor is available. Analyzing is very good when we can animate the result. Right click, animate. Sweep time is available, just go for OK. It will take some time to progress the result or to assemble the result, and it will provide us an animation. Since we have gone for nearly 100 time steps, 10 time steps. Hence, it will take some time to provide me the result. Let me go for fit all. This is the, you can say, magnetic field arrangement in my stator. You can see, previously I was saying that the stator magnetic field and the rotor magnetic field will, you can say, will not be parallel at any point. Okay, though they are coming, you can say the stator magnetic field frequency is followed by the rotor magnetic field, but they will never be aligned to each other, because that will produce zero torque, and we don't want zero torque in our motor. And this is how the magnetic field is rotating in our motor, because of the phase supply that we are providing. Now, magnetic intensity. I want to see the magnetic intensity. Magnetic field lines or flux lines we have seen. Now the intensities, that means at which point, what is the intensity of magnets or magnetic field that I have. I can see that from my magnetic H1 curve. You can see magnetic intensities. This is showing me the magnetic intensities at various regions. Okay. This animation is showing me the magnetic intensities at various regions. Magnetic intensities are very high near the rotor, and that is what we need. There should not be any high magnetic intensities outside of the rotor or outside of the stator or in the stator, but the magnetic intensities would be very good near the rotor. Let me plot the energy. Let me animate the energy that is utilized. So by analyzing all these things, we can find out whether the motor that we have designed is working correctly according to the specifications that we have provided. That is one thing. Second thing is, the motor, or you can say the motor energy and the motor losses are not that high. The energy that the motor is consuming and the losses that the motor is suffering from, those should not be very high. First thing is, the specification that we have provided, the motor is up to that specification or not in this design. That is the first thing that we are analyzing in here. Second thing is the energy consumption and the losses that the motor is suffering. That should not be very high. You can say these are the energy consumption regions. Maximum energy is consumed in rotation and you can say intersection of the magnetic fields. Though the RPM of my motor is not that high, hence energy consumption is not that, I can say energy consumption is good, or you can say it is nearly 2.3 joules per meter cube, but it is well distributed throughout my geometry. Let me plot the ohmic losses. Since we have not considered the winding losses, the ohmic losses will not be that prominent in the sections, since I have not provided any winding losses. It will take some time. It will not take some time, it will just take 20 to 30 minutes depending on the amount of time steps that you have used. I have used only 10 time steps, hence it will take only 15 to 20 seconds or 30 seconds to plot the animation. So these are my ohmic losses. Okay, ohmic losses at my windings and my, since I have not gone for any winding loss, the ohmic loss is only because of the resistance of the windings. And you can say when the current starts to flow, there is some high amount of resistance. Once the current is flowing, then the resistance decreases. It is just because when we switch on, we have the highest peak in current, and when there is highest peak in current, there will be some resistance that will be provided to change the state of the current. Because the current was 0, when we switch it on, the current is very high, so the resistance will also increase. So this is all in this motor designing session. In the next session, we will go for studying different types of powertrain arrangement that are available for our electric vehicle. Thank you. Hello everyone, welcome back. In the previous sessions, we have discussed what are the various types of motor technologies that are available to be installed in electric vehicles and how we can control them. What are the various types of controllers that are available in order to control the motor systems, their efficiencies and their working principles. Now, whenever we install a motor in an electric vehicle, the power of the motor needs to be delivered to the wheels so that the vehicle can be driven. So that is done by the propulsion system. Or we can say the propulsion system is a system that comprises of a power generating device and a power delivery device. Generally, the motor is a power generating device that can control the torque and power output or RPM output to the wheels, and that torque and RPM is supplied to the wheels through powertrain. So the whole propulsion system consists of motor, engine and the powertrain. So let us discuss in details what are the various types of propulsion systems that are available for electric vehicles. First, let us learn what are the various types of EVs that are currently running on the market. EVs can run solely on electric propulsion or they can have ICE working alongside with it. The electric vehicles that completely runs on electric propulsion, they are battery electric vehicle or full electric vehicle. If we have a IC engine installed in that vehicle, then that becomes a hybrid electric vehicle. Having only batteries as energy source constitutes the basic king of EVs. But there are kinds that can employ other energy source mode. This is basic, this is not king, this is kind. Basic kind of EVs. But there are kinds that can employ other energy source modes. They are called hybrid EVs. If we have only batteries as the primary power source and there is no other way to generate power inside the vehicle, then we call them as basic EVs or full electric vehicles. If there are certain other source of power generation inside the electric vehicle, then we call them as hybrid EVs. Not only engine, if we install you can say solar panels, if we install fuel cells inside the EVs in order to generate additional power to recharge the batteries. Then those type of EVs are also known as hybrid EVs. The International Electrotechnical Commission Technical Committee proposed that the vehicles using two or more types of energy source, storage or converters can be called as hybrid electric vehicles, as long as at least one of those provides electrical energy. That means your vehicle may have various types of power generating devices, a fuel cell, a engine, let's say any type of engine, thermal engines, then not thermal engines, any other type of nuclear engines, let's say. But if any one of those power source are using electrical energy, or they are producing electrical energy to be used in order to drive the vehicle, then we can call them as HEVs, hybrid electric vehicles. This makes a lot of combination possible for EVs like ICE and battery and flywheel, battery and capacitors, and battery and fuel cells. So these are the various types of power generating or power source combinations. ICE with a battery, two power source, one is chemical, another one is thermal, battery and flywheel, chemical and mechanical, battery and capacitors, chemical, battery and fuel cells, chemical and also chemical. Various combinations of power source inside a electric vehicle. Because of these reasons, the EVs can be categorized into various types of models. First one is a battery electric vehicle, hybrid electric vehicle, plug-in hybrid electric vehicle and fuel cell electric vehicle. So let us discuss about these categories of vehicle in details. What is a battery electric vehicle? EVs with only batteries to provide power to the drivetrain are known as battery electric vehicles. That means drivetrain means what? Drivetrains, you can say, is a combination of motor and powertrain that drives the vehicle. So if batteries are only the power source to run the motor or to run the drivetrain, then they are known as battery electric vehicles. Battery electric vehicles have to rely solely on the energy stored in the battery packs. The range of such vehicles depends directly on the battery capacity. Typically, they can cover 100 to 250 kilometers on one charge, where the top tier models can go a lot further from 300 to 500 kilometers, depending on the kilowatt rating of your electric vehicle. If your vehicle is 20 kilowatt, then it can run for nearly 100 to 250 kilometers. 30 kilowatt, more than that. 40 kilowatt, little longer than that. 60 kilowatt, the battery becomes too heavy to be used for passenger vehicles. 60 kilowatt batteries can only be used in commercial vehicles. These ranges depends on the driving style and condition, vehicle configuration, road conditions, climate, battery type and age of the battery or age of the vehicle. Charging time of battery electric vehicles depends on the charger configuration, its infrastructure and power operating levels. Battery electric vehicles, so they have to be charged from the grid only. Internally, there is no charging system available. Why? There is no other power generating source available. So they can only be charged externally from the grid or by using any solar devices. Then what is the power delivery arrangement for a battery electric vehicle? There is a battery, there is an inverter, there is an electric machine, that is a motor, there is a single speed gear and differential. Battery, the power source or the powerhouse. Inverter, the power delivery. That means the battery, if the battery will directly discharge to the electric motor, then we cannot control the efficiency of the discharge. For those reasons, inverters are used. So that depending on the amount of potential and current that is needed by an electric machine, the inverters can supply the required amount. there is a single speed gear. Directly if we will be connecting the motor to the wheels, then at certain conditions, the motor or the drivetrain cannot be tuned properly. Certain high torque situations, not RPM, but high torque situations, the electric motor or the electric machine cannot be relied upon. Hence, there is always a single speed gear to increase the torque output of the motor during any required condition. And differential. Obviously, four-wheeler, for a correct cornering or for perfect cornering, we need differential, and differential has to be installed in any four-wheel electric vehicle. Then hybrid electric vehicle. After battery electric vehicle, we have hybrid electric vehicle. Hybrid electric vehicles employ both an ICE and an electric powertrain to drive the vehicle. The combination of this can come in different forms. HEVs uses the electric propulsion system when the power demand is low. When the power demand is low, that means I have to drive inside a urban, or I have to drive it inside a city or urban area. Then the power demand is low because of the traffic. Hence, electric propulsion system can be very well utilized in those situations. It is of great advantage running at low speed conditions like urban areas. It also reduces the fuel consumption as the engine stays totally off during the idle periods. When higher speed is needed, the hybrid electric vehicle switches to ICE. The two drivetrains can also work together to improve the performance. Mechanical couplings are used so that engine along with the motor can drive the vehicle simultaneously. Hybrid power systems are used extensively to reduce or to completely remove the turbo lag in turbocharged cars. There is a turbo lag. What is the turbo lag? Since the RPM of the turbos has to be changed rapidly. If from slow moving I have to increase it to, you can say from lower RPM to higher RPM to lower RPM, then there is a lag. Because if the turbos are rotating at a very high RPM, you want to, and your exhaust gas is producing very low RPM or very low, not pressure, thrust force. Then there is always a turbo lag because of the inertia of the turbo blades. But in hybrid power systems, those turbo lags can be completely eradicated. Remember, this turbo lag, if you ask, sir, turbo lag is there, but then why don't I feel it on vehicles? All of the vehicles that have turbochargers installed, they all have turbo lags. Some of them have a greater turbo lag, some of them will have a smaller turbo lag, depending on the inertia of the blades, rotating blades. It enhances performance by filling the gap between the gear shift and provides speed boost when required. You don't have to shift gears in hybrid electric vehicles. Those are automatically managed by the drive system. And it provides an instant speed boost whenever it is required. The ICE can charge up the batteries. Hybrid electric vehicles can also retrieve energy by means of regenerative braking. The ICE, along with driving the vehicle, can also charge the battery. HEVs can also retrieve energy by means of regenerative braking. As I have said earlier, that generally in hybrid electric vehicles nowadays we are using engines in order to recharge the batteries. And the electric machine or the electric motor is solely responsible for driving the vehicle. Why is that? It is because we know when engine is used to transmit power to the wheels, lot of losses are taken into account. Or there is lot of losses, frictional losses, heat losses, sound losses, all those type of losses. But if the ICE is used only to recharge the battery, then those losses can be neglected or can be prevented, hence increasing the efficiency of the engines or the output of the engines. Then what is the power delivery architecture for a hybrid electric vehicle? During starting of the vehicle, the ICE runs the electric motor and the electric motor recharges the battery. Okay, electric motor can also be used as a generator. We know electric motor can be used as a generator. Generally, starting is done through ICE. ICE will start the vehicle. It will also run the powertrain and it will also use the electric motor as generator to recharge the battery. This is the basic, you can say, run for a hybrid electric vehicle. You can switch. So, during the starting of the vehicle, generally the batteries need to be primed. Hence, it is not discharged, rather it is charged. And the starting is done by the ICE only. You can switch between motor and ICE during the starting, but generally recommended that ICE is to start the vehicle. Then stopped condition. In stopped condition, there is no power flow. The batteries are switched off. Electric motor is not generating any electricity, nor ICE is running. During passing means overtaking. For overtaking, you need a lot of torque so that you can accelerate faster. You need lot of torque so that you can accelerate faster. Hence, both engine and electric motor are driving the powertrain, and battery is supplying electricity to the electric motor. IC engine is now running completely, or you can say it is not charging the batteries nor it is running the electric motor. ICE is completely providing all its power to the drivetrain only in combination with the electric motor. Then during braking, the ICE is cut off from the electric motor. The powertrain will supply power to the electric motor. Means in here the electric motor will behave as a generator. Remember, the rotation of the electric motor does not switch. Means the direction in which the motor was rotating, it is rotating, but the current flow direction is changed. Some of the diodes are used that generally restricts any back EMF that is produced by the electric motor. Those diode directions are reversed. Not diode directions are reversed, but the current flow directions are reversed by passing it through some other diodes, and that can recharge the battery. Then cruising. During cruising, you can say we need a constant speed. And cruising is generally done outside of urban areas, where we generally opt for a certain higher speed and optimum change in speed or optimum control of the speed, for which your ICE will be running the electric motor or it will be recharging the battery, and ICE will also help in running the powertrain. This is the cruising. Then HEVs are primarily ICE driven cars that uses an electric drivetrain to improve mileage for performance enhancement. While starting the vehicle, the ICE may run the motor as a generator to produce some more power and store it in the battery. You can say we are talking about starting of the vehicle. It is always recommended to start the vehicle with ICE rather than a motor, so that a priming can be done on the batteries. During overtaking, a boost in speed is required. Therefore, ICE and the motor both drives the powertrain. That is our passing. During braking, the powertrain runs the motor as generator to charge the battery by regenerative braking. While cruising, ICE runs both the vehicle and the motor as generator which charges the battery. Cruising means you are outside of urban area. Some level of pollution can be handled in those situations. If you are inside an urban area, strict pollution norms has to be maintained. So, the next category of electric vehicles are plug-in hybrid electric vehicles. The PHEV concept arose to extend the all-electric range of hybrid electric vehicles. It uses both an ICE and electric powertrain like a HEV, but the difference between them is the plug-in hybrid electric vehicle uses both electric propulsion as the main driving force, so these vehicles require a big battery capacity than the HEVs. So, in hybrid electric vehicle only that we were studying in the previous slide, in that both ICE and the motor were driving the vehicle. But in a plug-in hybrid electric vehicle, the motor is the driver. The drivetrain is the main driving force. Hence, a larger battery pack is required. A larger battery pack is required. Why is that? Because now the engine is not assisting the motor during any type of overtaking or steep gradient climb. The engine is not helping the motor, rather only the engine is used to recharge the batteries. Hence, a bigger battery is required, or the bigger battery capacity is required to provide the necessary power and torque, or necessary power only. HEVs start in all electric mode. You can say they start in all electric mode, not like you can say not in ICE mode, that was in hybrid electric vehicles. Runs on electricity, and when batteries are low, charger is calls, or you can say charge is calls on the ICE to provide a boost or to charge the battery pack. The ICE is used here to extend the range only. The plug-in hybrid vehicles can charge their batteries directly from the grid. In hybrid electric vehicle, remember, there is no external charging system. The hybrid electric vehicle that we are seeing in here, it has no external charging system. The batteries are only charged by the ICE. You cannot recharge the battery from the grid. Only you can recharge the battery from the ICE. But in plug-in hybrid electric vehicles, there is a additional charging system that is installed inside the battery or inside the vehicle, connected to the battery. And that charging system can utilize the power from the grid in order to recharge the batteries. Plug-in hybrid electric vehicles can charge their batteries directly from the grid. They also have the facility to utilize regenerative braking. PHEV's ability to run solely on electricity for most of the time makes its carbon footprint smaller than HEVs. Some of the examples are Chevrolet Volt and Toyota Prius is well known plug-in hybrid electric vehicle available in the market. Remember, in plug-in hybrid electric vehicle, IC engine is solely used for recharging the batteries. Then after we have fuel cell electric vehicles. Fuel cell is not a new concept, it is an advanced concept. In order to have a fuel cell passenger electric vehicle, it is a bit difficult because of the storage of oxygen and hydrogen. Though oxygen can be directly extracted from the atmosphere, storage of hydrogen is problematic because hydrogen is the smallest element that is available. Containing a hydrogen is difficult. We have to use heavy elements in order to contain hydrogen, and the containers, when they are built out of heavy elements or heavier elements, they tend to weigh a lot, thereby reducing the efficiency of a passenger vehicle. But fuel cell electric vehicles are very much used in large commercial vehicles like bus, trucks, etc. Fuel cell electric vehicles got the name because the power source of such vehicles are fuel cells that use a chemical reaction to produce electricity. Hydrogen is fuel of choice for fuel cell electric vehicles to carry out the reactions, so they are often called hydrogen fuel cell vehicles. Fuel cell electric vehicles carry the hydrogen in special high pressure tank along with oxygen which it requires from the air. There is an oxygen extraction unit that is installed inside those vehicles so that very pure, or you can say a pure quality oxygen can be used in order to produce the necessary energy along with hydrogen. Electricity generated from fuel cells goes into an electric motor which drives the vehicle. Excessive energy is stored in storage system like batteries or supercapacitor. A fuel cell, remember, a fuel cell can be directly used to supply energy by using some inverters as well as electronic devices that can maintain the balance of flow. But a fuel cell can directly run an electric motor. They can produce very high density power. The power density of fuel cells are very good. The power delivery capacity, a specific power. And if any additional energy is getting generated, then those are stored in batteries and supercapacitors. Fuel cell electric vehicles produces only water as the byproduct of its power generation process which is ejected out. Advantages of fuel cell electric vehicles are they can produce their own electricity which emits no carbon, enabling it to reduce its carbon footprint further than any other electric vehicle. Remember, the electric vehicle that we are charging or that we are charging from the grid also utilizes certain type of thermal energy produced from coal or any other petroleum product, and that supply or that generates carbon dioxide. So EVs that are charged from grid do have some carbon footprint. No, rather you can say they don't have any direct carbon footprint, but obviously they have certain carbon footprint. But fuel cell electric vehicles can run solely, or you can say, sorry, my comparison is a bit confusing. Fuel cell, you will be asking that, sir, for hydrogen extraction also we need, you can say, energy from grid. Yes, we do need, but the amount of energy that is generated, or you can say that is needed in order to separate hydrogen from oxygen is very less than that is needed for charging a EV. So overall, the carbon footprint for a fuel cell electric vehicle is less than a electric vehicle or hybrid electric vehicle. Refilling these vehicles takes the same amount of time required to fill a conventional vehicle. The only problem in hybrid, I can say, fuel cell electric vehicle is refueling. Refueling hydrogen is very dangerous. Refueling hydrogen is very dangerous. Though refueling petrol is also dangerous, but you can say refueling hydrogen is more dangerous than refueling petrol. Hydrogen is a very combusting, I can say, substance. Your petrol will catch fire, it will never explode. Though if it is kept in a container, it will explode. But hydrogen will start exploding the moment it catches fire. And the rate at which the fire is transferred in hydrogen is very fast. So this is the general architecture of a fuel cell electric vehicle. Air is taken, or you can say extracted from the atmosphere. Hydrogen cylinder, you can say we have hydrogen cylinder to contain hydrogen. Then there is a fuel cell device that uses hydrogen and oxygen to generate electricity. The fuel cell device transmits or delivers its power directly to the motor. If it is generating any additional power, then that is supplied to the auxiliary power source, and the byproduct is water. Now, since we know what are the various categories of EVs, like hybrid full electric vehicle, hybrid electric vehicle, plug-in hybrid electric vehicle, and fuel cell electric vehicle. Now let us know various types of powertrain combination that are used in electric vehicle. Various types of powertrain combination that are used in electric vehicle. EVs have different configurations. It can have a gearbox and a clutch that allows high torque at low speed and low torque at high speed. Mechanical interaction can be further reduced by placing the motor inside the wheel to produce in-wheel drive. Planetary gear systems are employed here because of their advantage of high speed reduction ratios and inline arrangement of input and output shafts. HEVs use both an electric propulsion system and an ICE. Various ways which show these two can be set up are summed up into 4 categories. So how a ICE and an electric propulsion system are arranged inside a vehicle can have various types of combinations, or we can have various types of setup using electric propulsion systems and ICE. What are those? Series hybrid, parallel hybrid, series parallel hybrid, and complex hybrid. Series hybrid, parallel hybrid, series parallel hybrid, and a complex hybrid. So let's see in details what are all these what are all these powertrain combinations. First is a series hybrid. This configuration is the simplest way to make all of the HEVs. The motor is connected to the wheel and the engine is used to run a generator which produces the electric power. It can be put as an EV assisted by a ICE generator. So there is a fuel tank, there is a ICE, there is a generator, there is a rectifier. We all know the working of a rectifier. The rectifier is used to rectify any ups and downs in current flow. You can say it supplies its energy to motor controller and then traction motor and mechanical transmission. So you can say it is connected in series to the motor. The engine in here is not taking part in driving the vehicle. Rather, the work of engine in a series hybrid is only to run the generator. What are the advantages of this system? Efficient and optimized power plant. Possibilities for modular power plant. Optimized driveline. Possibility of swift black box service exchange. What is this black box service exchange? That means the system can be very well replaced completely. If any of the portion of the system is damaging, it can be very well exchanged. Long lifetime, mature technology, fast response and zero emission. What are the disadvantages? A large traction drive system is required. Why? Because only the motor is driving the vehicle. Requirement of proper algorithms, multiple energy conversion steps. So you can say the energy conversion steps are multiple. Engine, generator, rectifier. Rectifiers and motor, rectifiers are not needed. Some you can say these are additional power source. Generator is also additional because we can use the motor as generator also. So why we have to install additional generator? Motor controllers are required in all of the electric vehicles. Then we have parallel electric vehicle. In this configuration, both ICE and the motor is parallel to the wheels. Either one of them or both of them take part in delivering the power. It can be considered as an ICE vehicle with electric assistance. So the series was a electric vehicle with ICE assistance, or it can be put as an EV assisted by a IC generator. But a parallel hybrid can be considered as an ICE engine vehicle with electric assistance. The energy storage in such vehicles can be powered by the electric motor through regenerative braking or by the ICE, while it produces more than the required power to drive the wheels. You can say the energy storage that is there in this type of vehicles generally runs the electric motor and can also be run through regenerative braking or by ICE. And when it produces more power, it can be driven to the, or you can say it can be provided to the wheels. You can say fuel tank, engine. There is a mechanical coupling that can drive the, you can say that can take input directly from the engine or from the motor and also simultaneously from engine and motor. What are the advantages of using this system? Capable of attaining zero emission. If we use only the traction motor in place of engine, attaining zero emission, it can attain nearly zero emission. Economic gain and more flexibility. Economic gain and more flexibility. Why it is more flexible? It is because now we can have various driving scenarios. I can drive very well in urban areas, I can drive very well out of urban areas also. Because it is engine assisted, so I will be getting a full feel of the engine vehicle as well as a electric vehicle. Hence more flexible. Disadvantage, they are expensive because of certain mechanical complex that are introduced in these vehicles. Complex control. The engine and the traction motor has to be synced properly. Only then there will be, or you can say only then we can prevent losses during transmission. Hence, they have a very complex control. Requirement of proper algorithms to control the power output or to control the running of the motor and engine also. Because engine has a ECU that runs an algorithm only. Need of high voltage to ensure efficiency. Since the engine is producing a lot of torque, so the motor, in order to run in sync with the engine, that means the engine produces a lot of power. So if the motor has to be synced with the engine, then there is need of high voltage, so that a high amount of current can be pushed through the circuit. After that, we have series parallel hybrid. What are series hybrids? In an effort to combine the series and the parallel configuration, these systems acquires an additional mechanical link compared to the series types, or an extra generator as compared to parallel types. This provides more advantage of both the systems, but is more costly and complicated. You can say in series, we have the, you can say, flexibility of both series parallel hybrid. In series parallel hybrid, we have the flexibility of both to run as a series hybrid system and also to run as a parallel hybrid system. But these introduce a lot of complexity in the system and also costly. It is costly. Complication in the drivetrain is caused to some extent by the presence of the planetary gear unit. You can see there is a planetary gear system that is used in here. Okay, there is a planetary gear system that is used in here. The main input, you can see there are two shafts. This is the input shaft, and you can say we have a, this is the output shaft and we have an input shaft. Generally, the input shaft is the engine input. This shaft is the input from engine. This goes to the generator. And this sun gear or ring gear is connected to the traction motor. Okay, it is connected to the traction motor. Okay, there can be three ways of power delivery in here. There can be various ways of power delivery in this planetary gear system. The sun gear is connected to the ring gear. You can see this is the sun gear, then planetary gears, then the ring gear. The outside one is the ring gear. Sun gear is connected to the ring gears through the planetary gears. The IC is coupled to the planetary carriers and the pinion gears keep the whole system connected. These small gears are the pinion gears. So, engine, you can say we don't need to have, you can say, various types of other reduction methods. In series hybrid, the engine was running the generator. In parallel, the engine is running the drivetrain. If we use you can say planetary gear, then the engine can also be used to run the drivetrain. The engine can also be used to run the generator. So, this can be a complete series parallel hybrid. If we use powertrain, then the engine can run the generator. As in series hybrid, it can also run the powertrain along with motor as a parallel hybrid. So, both of the mechanisms can be achieved by using a planetary gear set. Series parallel hybrid. Less complex alternative to this system is to use trans motors, which is a floating stator electric motor. What is this trans motor? This is a type of motor. Okay, I will be discussing about this motor. In this system, the engine is attached to the stator and the rotor stays connected to the drivetrain through the gears. You can say this trans motor, the engine is attached to the stator and the rotor stays connected to the drivetrain through the gears. Trans motor, that means engine motor coupling. Completely the engine and motor are coupled. Completely the engine and motors are coupled. The motor speed is the relative speed between the rotor and stator, and controlling is adjusted the engine speed for any particular vehicle speed. So, there is a stator and there is a rotor in the motor. The relative speed between the stator and the rotor generally is adjusted to the engine speed. That means the engine is driving and the stator and rotor are also, the rotor is also driving the vehicle. Both of them are connected through a transmission lock. But in here, there is no controller, motor controller. The engine is directly connected to the motor. That is why it is a trans motor. And it uses a mechanism called floating stator electric mechanism. That means this motor can also be used to start the vehicle. So, the engine is there, transmission line is there, transmission line is locked to traction motor. Okay. And there are two types of motor controller. One is to run the trans motor and another one is to run the main motor. There is a trans motor and there is a main motor, remember. Then complex hybrid. After a less version of series parallel hybrid, these versions are generally not used. Okay, this series parallel hybrid, this is used. Parallel system, parallel gear series parallel hybrid is used in various vehicles. This trans motor is a ongoing technology. Okay, it hasn't seen any. Some of the vehicles are there, they use this trans motor. Okay, but not a mature technology. Complex hybrid. This system has one major difference with the series parallel hybrid. It allows bidirectional flow of power, where there is a series parallel can only provide unidirectional flow. These complex hybrids can go for bidirectional flow of powers. You can see there is an engine, there is a power split device, there is an electric motor generator and there is an electric motor generator. So what is this? We can drive the powertrain from the engine. We can also drive the powertrain through motor, and if required we can also drive the motor from the engines also. Various ways are there. You can see this power split device, the motor can run this power split device, this power split device can run the motor. This final drive to wheels, you can say, can also run the motor during regeneration, and the motor can also supply the power to the wheels. So both of them, you can say, they can flow in both the direction. This motor can also run this motor, this secondary, let's say this is motor 1 and this is motor 2. So motor 2 can also run the motor 1 as generator, or there is no need of generator actually. The motor 2 can also act as a generator and it can supply its energy to storage device. This power split device can also run this electric motor as a generator, helping the energy storage device. So if this you can say this second motor is switched on to supply energy to the drivetrain, then the first motor is used as a generator to store energy. If there is regenerative braking, then this motor 2 can be utilized as a power generating device. And this, you can say, so this is the bidirectional flow of power. The power can flow in any one direction. And yes, this motor 2 can also run the power split device so that it can assist the engine. Means this motor 2 and motor 1, both of them can assist the engine. High complexity and costs are the drawback of system, but it is adapted by some vehicles due to dual axle propulsion. This is very important, dual axle. That means you can say you can have both front wheel and rear wheel also. Constant variable transmission CVT can be used for power splitting in complex hybrid systems or choosing between power source to drive the wheels. Two methods of power splitting: input splitting and complex splitting. We have seen about, you can say, input splitting. Input splitting means any inputs to any powertrain device can be split. You can say in here it can be split between electric motor and the engine. And the complex splitting is, you can say, when the engine is running the vehicle and the vehicle has to regenerate. So the motor 2 is utilized in order to regenerate. And at that time, the engine has to be cut off from the drivetrain. So this motor 1 can also be used as a generator. Both of them can be used as a generator. So this is complex splitting. Input splitting got the name as it has power splitting device placed on the transmission input. This system is used by some Toyota and Ford models. Such power split EVs require two electric machines, wheels and engines, and a planetary gear. Combining all of them, it can have 24 different ways of splitting. If another planetary gear system is used, it can have a 1000 way of power splitting. Not required this much. Okay. For a bigger electric vehicle, for a commercial electric vehicle, it is required, but not for passenger electric vehicles. Four-wheel drive configuration. You can say dual axle module, what I have said. You can say we can have four-wheel drive configuration, can benefit from using two motor hybrid configuration, as it removes the need of a power transmission system back to the wheels and provide advantage of energy reproduction by means of regenerative braking. So now in this session, we have learned what are the various types of or categories of EVs that are available and the various types of powertrain combinations that these EVs can have. Some of these powertrains are very efficient, some of these powertrains are not that efficient. But in recent future, what we will be seeing is we will be seeing mostly the series and parallel hybrids. Some of the complex hybrids will also be seen and series parallel hybrids also. All of them will be seen, but mostly series and parallel hybrids. Thank you. Hello everyone, welcome back. In the previous session, we have discussed what are the various types of EVs that are available and various powertrain combinations that can be installed on those EVs. Today we will discuss the dynamics of the vehicle. Whenever we develop any type of vehicle, any road vehicle, either a two-wheeler or a three-wheeler or a four-wheeler, the dynamics of the vehicle has to be taken care because the dynamics will represent how well the vehicle is responding to situations. If there is any bump, if there is any drop or any pothole on the road, if there is any corner, if uphill, downhill, bank, overtaking or in traffic areas. Okay, so all this response of the vehicle are managed by the dynamics of the vehicle. If the vehicle is dynamically very good, then its response is also very good. That means we can maintain very well response or we can get very well response from the vehicle. I want to overtake, okay, gear shifting, then turning, you can say using the steering wheel, we can very easily overtake the vehicles. If the response is sluggish, if it is not responding properly, for overtaking, I can't have that confidence. For cornering, I can't have that confidence. For uphilling, downhilling, banked roads, I can't get that confidence. It is because my vehicle is not responding. Though I will be, after some time, I will be acquainted with the driving of the vehicle. But still, I will always underperform while driving my vehicle. The rider has to perform well while driving its vehicle. I am not saying about any track driver. The normal road driver, passengers. Let's say I am driving a passenger, or you can say normal, a simple vehicle, not a track vehicle, not a racing vehicle. But still, I am driving on the road. So, I should be able to handle my vehicle properly. In case of any emergency, I should have a faster response in my vehicle. You can say my vehicle should respond to me very fast in case of any emergency. Today I am late for office, I want to drive the vehicle bit fast. Today there is some, you can say I am late for any other thing, or today I am going for, you can say I am off-roading my vehicle. So, it should respond depending on the requirement of the rider. For these reasons, the dynamics of the vehicle has to be taken care properly. So, let's start with the dynamics of the vehicle. The first one that we will be considering in here is the steering geometry of the vehicle. Any vehicle, two-wheeler, three-wheeler or four-wheeler, if we can't direct the vehicle along the direction that we want it to move, then it is useless. It will just go in a straight line, then what is the use of that vehicle? If we can't direct it, it will be completely useless to run the vehicle on this planet, where the roads are not straight, the land, you can say slopes of the roads are not straight, the terrain is not uniform. Hence, we always have to maneuver the vehicle in different directions, for which the steering geometry of the vehicle should be very well designed. Now, let us know some of the basic geometries that are related to our steering. The first one is, in order for a car to turn smoothly, the inside wheel must travel on a smaller radii arc than the outside wheel, allowing the car to turn. So, what is this inside wheel must travel on a smaller radii arc than the outside wheel? Let's see. When our vehicle is taking a turn, then the inside wheel is on a smaller radii than the outside wheel. This is what we are talking about. The inside, you can say this is a turn. Inside wheel radius is smaller than the outside wheel radius. So, in order to maintain optimal turning speed, the inner wheel has to rotate slower than the outer wheel because the outer wheel is tracing a longer radius. Hence, it has to rotate faster than the inner wheel because the inner wheel is taking a small turn while the outer wheel is taking a large turn. Okay, the outer wheel is taking a large turn. So, the outer wheel is rotating faster than the inner wheel because the outer wheel is tracing a larger radius. than the inner wheel. So you can say for any small displacement, the inner wheel will rotate once while the outer wheel will rotate twice. So because of this, there is traction difference. The inner wheel, since it is rotating slower, it will have higher traction than the outer wheel that is rotating faster. Now if you ask, sir, how there will be a traction difference? For that we have to know the properties of rubber or how the pressure is distributed in a tire. When it is rotating slower, the pressure difference, not pressure difference means, I will be saying out the pressure that is generated on the tires or the stress or that is generated on the tires, it varies slowly, while in outside tire it varies faster. Hence to capture or to grip the road, it is, or you can say it is getting less time to grip the road. For the outer wheel, since it is rotating faster, it has less amount of time to grip the road, while the inner wheel has more amount of time to grip the road. Hence, traction on the outer wheel is lower than the traction on the inner wheel. Now, our vehicle is a heavy body. It weighs nearly 1000 kgs. Our vehicle is a heavy body. It weighs nearly 1000 kgs. Yes or no? So, when there is centrifugal force on these bodies, so our body will slip out if there is a very less amount of traction on the outside. So how our vehicle will be rotating? Let me show you. Let's say this is the arc on which our vehicle has to turn, or this is the road on which our vehicle has to take a corner. So vehicle is slipping on sideways because of less amount of traction on the outer wheel. So it will take a larger turn in order to capture this small turn. Or if I want to just turn my vehicle along this path, the vehicle will take a larger path. Why is that? It is because the outside wheel traction is less than the inside wheel. So the vehicle will skid. Okay. The vehicle will skid. If you ask, sir, why the vehicle will skid? It is because since the outside traction is less, this is the turn. So, in order to properly capture the turn, the vehicle should always move on the tangent. But since the inner wheel has more traction than the outer wheel, so the tangents are, there are no more, you can say there are no more tangents. Okay. They are off tangent. So now they will rotate in a larger radius. And how this can be achieved? How can we rotate the vehicle along this track? This is done by turning the inside wheel more than the outside wheel. That means if we turn the inside wheel more than the outside wheel, now they are at same angle. Now what we have to do is we have to turn the inside wheel more than the outside wheel. The inside wheel and outside wheel have the same orientation. They have the same orientation, but in order to achieve a proper turning, the inside wheel has to rotate more than the outside wheel. This geometry is used to avoid the need for tires to slip sideways when following a path around a curve. So if we rotate the inner wheel higher, or you can say if we turn the inner wheel more than the outer wheel, then we can very well capture the curvature of the road without going for any sideways slip. Because the energy that the body was losing because of reduced traction. Now that energy, you can say, now since we are we are tightening the turning radius of this inner corner. We are tightening the turning radius of this inner tire than the outer tire. If both of them are have similar, you can say similar steering angle, then they will have, you can say, same amount of radius of curvature, for which the effective radius of curvature will be less than that is required. So what we do, we increase the radius of curvature for the wheel, rotating wheel, and we tighten the cornering efficiency of the inner wheel than the outer wheel, so that we can overcome those inefficiencies and we can make a very good turn. The geometrical solution to this is for all wheels to have their axles arranged as radii of the circles with a common center point. As the rear wheels are fixed, this center point must be on the line extended from the rear axle. Intersecting the axis of the front wheels on this line as well required that the inside front wheel be turned when the steering through a greater angle than the outside wheel. So let us see what is this Ackermann geometry. So this is the Ackermann geometry. The inside wheel, you can see it is turned more than the outside wheel. Our alpha is greater than beta. And when we perform this type of geometrical arrangement of the vehicle, then one thing we get is, if both of the wheels are same, or if let's say if both of the wheels have the same turning angle, and if we draw perpendiculars from both of the wheels, so they will be completely parallel to each other. We can't have a common center of rotation. Calculating anything without having a common center of rotation becomes very difficult. Calculating any turning radius, calculating any traction forces, calculating any slip angles will become very difficult if the axis of the two wheels are not intersecting at a point. So, if we just increase the angle of the inner wheel, now they can meet at a point. So, now we have two advantages of this system. First one is we tighten the inner turning radius, then when we extend the axis of these two, remember these are perpendicular, axis of these two wheels, then they meet at a common center of rotation that we can use to define the turning radius of the vehicle, and that center of rotation should match on the line running through the rear axle. So, this is what is a Ackermann geometry. All the vehicles should follow this geometry. That means the steering should be angled, or the steering angle increment should be in such a way that whenever we provide any complete turning, see this is the complete turning. Now this is not a, let's say sir, at 30 degrees will it meet, at 40 degrees will it meet, at 50 degrees will it meet? No. At 30-40 degrees you can say they will be meeting somewhere here, and yes, at each and every point they should meet on the rear axle only. That you can say the steering mechanism should be made in such a way that whenever we take any turn, even if a small turn of 5 degrees, 10 degrees, 20 degrees, whenever we draw normals, or you can say whenever we draw along the axis of the wheels, they should meet at the rear axle. And you can say this in here, this is the maximum. This is the maximum. So, this R is nothing but the turning radius at maximum wheel angle. When we have a wheel angle of 5 degrees, the turning radius will also increase. When we have a wheel angle of 5 degrees, the turning radius will also increase. 10 degrees again it will increase, it will decrease. 20 degree, 5 degree means it will decrease, 10 degree it will increase some more, 20 degrees it will increase some more. At maximum angle I will be having the minimum turning radius. You can say this is the Ackermann geometry. The inside wheel has a larger angle than the outside wheel. Then after, you can say in order to maintain proper dynamics of the vehicle, the 3 wheel angles has to be taken care of. First one is the toe, second one is the camber, and third one is the caster. So let us see what are the 3 wheel angles. First one is toe. What is toe? Toe is the angle between each wheels with relation to the longitudinal axis of the vehicle. Remember, toe is always seen from the top view. Toe is always seen from the top view. It is always measured when the car is static and measured either in degrees or millimeters. There are 3 types of toe setting. Let's see what is toe. So you can say this is top view. We have toe in, neutral toe, and toe out. What is toe in? When the front edge of the front tires are closer than the rear edge of the rear tires, it is toe in. When both of them are same, it is neutral toe. When the front edge of the front tires are farther apart than the rear edge of the rear tires, this is toe out. So these are the 3 toe settings. Let's see what are the advantages and disadvantages of this toe setting. Toe in is where the front edge of the front 2 tires are closer than the rear edge of the rear 2 tires. Front edge of the front tires are closer than the rear edge of the rear tires. Rear edge of the front tires. On the front of the car, toe in increases straight line stability. If I have toe in, you can see they are directed along the center axis of the vehicle. So this increases straight line stability. So toe in generally increases straight line stability. If your vehicle has some problem in steering or if it has some problem in dynamics, then generally we provide some toe setting to increase the straight line stability of the vehicle. This is because, okay, I will not be covering this point, excessive tire wear. So when there is toe, what will happen? There is excessive tire wear. Why is that? Why is there excessive tire wear? You can see in here, since if I draw a straight line in here, you can say, let's say I will be drawing like this. You can see this edge is always, you can say, will hit any bump, any drop, anything that comes first on the road. This edge will hit first, then this edge will hit. Both of the edges are not simultaneously taking the load. Whether the first, you can say this edge will take the load first, then it will respond, and then the second edge will take the load of the front tires. Hence, there is always tire wear on this front side. On this side, remember, for a vehicle with toe in, the outside corner of the front edge generally wears out more than the inside corner. So because of this thing, there is excessive tire wear in a toe in vehicle. Then another one is toe out. Toe out is where the back edge of the front 2 tires is closer than the front edge of the same tires. The back edges are closer than the front edge. This is toe out. Toe out decreases straight line stability. You can see it is diverging. Hence, it decreases the toe out straight line stability. When the wheel is disturbed in a straight line with toe out, pulling the wheel rearwards of the steering wheel. Okay, we will not be discussing. Okay. This decreases straight line stability as it makes the car develop a twitchy nature which can be uncomfortable at high speeds. So now there are some other benefits of toe in and toe out. Benefits, and you can say for toe in, there is an increase in straight line stability. But vehicle nearly understeers. Vehicle understeers in toe in. In toe out, there is no straight line stability. There is no straight line stability, but vehicle oversteers. What is understeer and oversteer? When the amount of response that you want from the vehicle is less than your expectation, then it is understeer. When the amount of response that you want from your vehicle or steering system is more than your expectation, it is oversteering. That means you want to turn the vehicle 5 degrees, the vehicle is turning 10 degrees. So this is oversteer. 5 degree of wheel input, of hand wheel, that is your steering wheel input, you can see you are getting 10 degree of wheel output. Then that is oversteer. That means the vehicle is responding more than you need. That is oversteer. If the vehicle is responding less than you need, then that is understeer. In toe in, generally the vehicle understeers. In toe out, generally the vehicle oversteers. In most of the race vehicles, we have oversteering setting, so that the vehicle will be understeering. You can say your track drivers can maintain or can handle very well this oversteering, or can maintain very well this toe out setting. But for passenger vehicles, generally neutral toe or toe in is used, because understeering on traffic, on roads is very good, not oversteering. Okay. So this is the benefits of using toe. After toe, we have camber. Camber angle is the angle between the plane of the wheel and vertical when seen from the front. Remember, camber is always seen from the front view. Camber is always seen from the front view. Now there are two types of camber setting: negative camber and positive camber. So let's see what is negative camber. You can see If the top edge of the tires are inclined towards the center of the vehicle, if the top edge of the tires, front tire or rear tire, if the top edge of the tires are inclined towards the vehicle, towards the center of the vehicle, then it is negative camber. If the top edge of the tires are inclined outside the center of the vehicle, then this is positive camber. Let's see what are the benefits of negative camber. Negative camber in general improves handling when cornering. That means your cornering entry will be very fast in negative camber, exit will be moderate. But the cornering entry, you will be entering a corner very fast in negative camber, but when you will be exiting the corner, it will be normal, or it will be just like, it will be slower than the entry. This works when the car is cornering, the lateral load transfer to the body causes the vehicle to roll. So what will happen? I have not said about roll, but let's see. So when there is a centrifugal force, the vehicle will roll to one side. So now the outside, there is an increase in traction on the outside of the vehicle. So a tight corner is maintained. When the vehicle will roll means it is rotating along its longitudinal axis. Okay, that runs from the rear of the vehicle to the front of the vehicle. You can see this is the roll motion. When the vehicle will roll, you can say there is a shift in load will shift from the, let's say this is the, from driver perspective, this is the right side and this is the left side. So the vehicle will roll from right side to left side, there will be shift in load from the right side to left side when there will be corner. So the outside wheel will have a greater traction, and this you can say improves the cornering stability and also the cornering performance of the vehicle. You can say when the car encounters roll, it raises the inside contact patch of the outside wheel. This reduces overall grip. This increases overall grip, increases overall grip. Now positive camber. Positive camber has no such riding benefits. It is only usually seen on road cars if there is a damage to suspension components, in most commonly used in heavy load application such as trucks, where when the vehicle is empty, the tires have positive camber. So when the vehicle is in normal operating load, the tires then settle to a neutral camber position due to camber gain of the system. So we generally see negative camber in auto rickshaws, in some of the vehicles. That means when the vehicle is not loaded, there is positive camber. When the vehicle is loaded, there becomes zero camber, or the vehicle has zero camber. So that to reduce the tire wear. When the vehicle is not loaded, tire wear is there, but it's very small. So positive camber is generally provided to those tires. When the vehicle will be loaded, then you can say tires will have zero camber, thereby reducing the tire wear. Then the third angle, remember, let me save the third angle, that is the caster angle. Caster is the measure of how far forward or behind the steering axis is to the vertical axis viewed from the side. Remember, caster is always viewed from the side view. Caster is always seen from the side view. Toe from top view, camber from front view, and caster from side view. If the top mount of the suspension is behind the axis of the wheel, then it is positive caster. If the top mount of the suspension is forward of the axis of the wheel, it is negative caster. If it is completely in line with the axis, then it is neutral caster. This is measured by drawing a line between the top and bottom pivots of the front upright. There are two types of camber setting. Negative camber. Negative camber is when the top mounting point of the control arm to the hub is in the front of the center line of the wheel and the bottom mounting point of the hub is behind the center line. You can see this is negative caster, when the top mounting is forward of the center line and bottom mounting is behind the center line. The only notable advantage of having a negative caster is that the steering input effort required is very low, making the steering very easy to turn. So for negative caster, the steering effort is very low. Hence, it is very easy to rotate the vehicle. So generally negative caster is provided on heavy vehicles, not on light vehicles. And heavy vehicles where the vehicle needs a lot of steering effort, negative camber is used to reduce the steering effort. Then positive caster. Positive caster is when the top mounting point is more rearward of the car than the bottom mounting point when looking at the side view. Positive caster creates a self-aligning torque. This increases the stability of the vehicle in straight line situation, increasing impotence at high speed. So what is this Self-aligning torque, remember, whenever you rotate the hand wheel or the steering wheel, it automatically comes back after a rotation. Why is that? It is because of this positive caster. When your wheels have positive caster, they have this self-aligning torque. But because of this self-aligning torque, the steering effort increases. Because whenever you will be providing some steering angle, it will always try to align itself. So you have to fight with that aligning torque in order to provide a steering input to the steering wheels. But because of that, the vehicle always comes back to a straight line position because of this self-aligning torque. So it has both advantage and disadvantage. Advantage is very good than disadvantage actually. For power steering, if your vehicle has power steering, you can very easily overcome this self-aligning torque. And this self-aligning torque is required that after you have taken a turn, you should not fight with the steering wheel to make the car straight. It should automatically come back. So that happens because of positive caster. The firm and stable steering provides the driver with confidence and allows them to drive at high speed lines as they are not fighting the steering wheel. Okay. Neutral caster, negative caster and positive caster. Remember, negative caster decreases the steering effort, but it also decreases, or you can say it also decreases directional stability of the vehicle. Means the direction in which you are pointing your vehicle, you can say vehicle will not maintain that direction properly, because it will, since the steering effort that is required is very less. First is that, and you can say this steering effort, this less steering effort will also sway the vehicle, or it will have some wave motion on the vehicle, or yaw motion. Let's say this is a line that the vehicle has to follow. The vehicle will go like this in negative caster. If the vehicle has positive caster, it will directly go like this. Okay, it will follow the direction very faster. Okay, if your vehicle has negative caster, there will be lot of yaw motion in order to achieve the direction. If it has negative caster, because the steering effort is less, means now the wheels can, you can say, there will be bump steer. Bump steer means you can say the wheel forces, the forces that are generated in the wheel, they can very easily disturb the steering. The wheels that are generated in the forces that are generated in the wheels, they can very easily disturb the steering, for which in negative caster you lose the directional stability. But in positive caster, since there is an aligning torque, this prevents any change or any disturbance to the wheel. It has an aligning torque. If there is any disturbance, it will automatically align. If there is any disturbance, it will automatically align. In positive caster, if there is any disturbance in the wheel, it will always try to maintain a straight line position. That means the wheel should always be straight, because aligning torque is there in order to maintain that straight line, or in order to maintain that, we can say, in order to maintain the wheel in a straight line, for which the directional stability of the vehicle is very high. If there is any road or tire forces that are acting, then or you can say if there is any force that is acting, automatically the tire will regain its original shape or original orientation, for which the stability is maintained, directional stability. But in case of negative caster, if there is any disturbance, the disturbance is maintained. Again, you have to use steering wheel to remove that disturbance. If again there is some road disturbance, that disturbance is maintained by the wheel. Again, you have to provide some steering input in order to reduce that disturbance. But in positive caster, automatically that disturbance is managed by the wheels. Hence, in positive caster, you have a very good directional stability, and in negative caster, the directional stability is lost. So, I will be concluding that in this session. So, in this session, we have seen how Ackermann steering affects the geometry of the steering, and how we can achieve 100% Ackermann steering. What are the three wheel angles that we need, that we have to consider while designing a vehicle? Toe, camber and caster. Remember, caster is a static wheel angle. That means once you have provided a caster, it will never change. But toe and camber, they are dynamic. That means during the driving condition, you will be having different toe settings and you will be having different camber settings. Or you will have changing toe angles and changing camber angles. Okay, so I am ending this session in here. Thank you.